the balance point between the Sun and Jupiter, where objects remain trapped for billions of years. Between the Sun and Jupiter, there are regions of space where the gravity of these two giant masses balances out precisely. These points, called Lagrange points, are true gravitational traps. In particular, Jupiter's L4 and L5 points have held thousands of asteroids in stable positions for billions of years. They don't fall toward the Sun or Jupiter, they remain frozen in their orbits. This creates a unique orbital structure within the solar system. These objects are known as Trojan asteroids, and they orbit the Sun at the same speed as Jupiter. Interestingly, they are not stuck to the planet, but move 60 degrees ahead or behind it. Since the gravitational forces of both bodies balance at that point, the asteroids can remain there indefinitely. They are like invisible passengers on Jupiter's orbital journey. So far, more than 12,000 have been identified. It is believed that these asteroids are fossils from the formation of the solar system. Because they are in stable and relatively undisturbed regions, they have not undergone as many collisions as the asteroids between Mars and Jupiter. This makes them ideal targets for studying the primitive composition of planets. NASA launched the Lucy mission specifically to explore them. It will be the first time we visit these ancient bodies up close. Another curious detail is that Trojan objects are not exclusive to Jupiter. Neptune, Mars, and even Earth have their own Trojans. In Earth's case, the first was discovered in 2010, named 2010 TK7. It moves in a horseshoe-shaped path, slightly shifting its position relative to the planet. It's a type of almost imperceptible orbital companion. But the concentration around Jupiter is by far the most remarkable. These gravitational balance points are so stable that space agencies use them to park probes and telescopes. The James Webb Space Telescope, for example, is located at Earth's L2 point, allowing for a free and constant field of view. It's a practical use of the same physics that keeps asteroids in place for ages. The combination of stability and isolation makes them ideal for long-term observations. By observing these points, astronomers also study the behavior of ancient collisions. Some Trojans are binaries, pairs of asteroids orbiting each other while also orbiting the Sun. Others have irregular shapes, as if they were fragments from impacts. Simulations show that these gravitational traps can, in some cases, even capture bodies coming from outside the solar system. The exact origin of these Trojans is still debated. Some models suggest they were captured shortly after Jupiter's formation. Others indicate they came from outer regions, brought in during a period of gravitational instability. What is known is that they behave like time capsules. They are practically intact since the planets formed. These bodies vary greatly in size. Some are less than a kilometer in diameter, others, like 624 Hector, are over 200 kilometers long and have an elongated shape like a cosmic peanut. Their diversity indicates that they likely did not form in the same place. This further increases their scientific value, as they may contain clues about various regions of the early solar system. The orbital behavior of these asteroids also serves as a natural laboratory for testing gravitational models. By studying their oscillations and long-term movements, scientists refine simulations of orbital stability. This even influences the planning of space missions and satellite safety. Understanding how bodies remain stable for billions of years helps build more durable spacecraft. Another intriguing point is that these asteroids do not follow perfectly circular orbits. They oscillate, vibrate, and form paths that resemble spiral bundles. This oscillation, called libration motion, is what allows their long-term stability. It's a dynamic, not static balance. They are constantly adjusting among the forces around them. Even though they are invisible to the naked eye, Jupiter's Trojans have considerable total mass. Estimates suggest that together they may exceed the volume of the asteroid belt between Mars and Jupiter. Still, because they are so distant and dark, they remain difficult to observe. That's why each new mission reveals unprecedented structures. In the coming years, the Lucy mission will fly by at least 8 of these bodies. The goal is to map, photograph, and study their mineral composition. It is expected that the data will reveal important chemical differences between them. This could confirm the hypothesis that they came from different parts of the solar system, and perhaps provide clues about the chaotic paths matter took before Earth existed.
A moon with active geysers that shoot water so high they create an entire ring around Saturn. Saturn's moon Enceladus seemed like an ordinary icy satellite until 2005. That was when the Cassini probe detected water vapor jets being expelled from its south pole. These jets were not small. They shot through space at incredible speeds, forming columns visible hundreds of kilometers above the surface. The discovery was one of the mission's most unexpected. Upon closer investigation, Cassini revealed that these jets came from fissures known as tiger stripes. These cracks cut through Enceladus's ice, releasing vapor, ice, and organic particles. The presence of internal heat was evident, which surprised scientists. Until then, it was not imagined that such a small moon could maintain significant geological activity. Even more impressive is the impact of these jets on Saturn itself. The material expelled from Enceladus escapes its weak gravity and ends up in space. Part of it enters orbit around the planet, feeding the E-ring, one of the largest in Saturn's ring system. In other words, this moon keeps an entire ring alive with its geysers. Cassini managed to fly through the plumes multiple times, collecting samples during its passes. Analyses revealed the presence of complex organic molecules, silica, and salt. This indicates there is liquid water beneath the icy crust, likely in contact with a rocky core. This scenario is ideal for chemical reactions that could support microbial life. Models suggest that Enceladus has a global subsurface ocean trapped between the core and the icy crust. The heat required to keep the water liquid may come from gravitational friction caused by Saturn. This type of heating, known as tidal heating, is also observed on other active moons, like Io. Enceladus's surface reflects almost all the sunlight it receives. This makes it one of the brightest surfaces in the entire solar system. Even so, beneath this gleaming exterior lies a dark, damp, and possibly dynamic environment. The contrast between appearance and interior is striking, and that is precisely why it has become one of the main targets of modern astrobiology. One of the big questions is, how can such a small body maintain an active ocean for so long? Enceladus is only about 500 kilometers in diameter, less than 1/5 the size of the Moon. In theory, it should have cooled billions of years ago, yet its internal heat persists, possibly fueled by a continuous cycle of gravitational flexing. This keeps the water in a liquid state and the crust active. Moreover, Enceladus displays patterns of cracks and smooth terrain that indicate constant surface renewal. This means that it is, in a way, rebuilding itself frequently. While most moons bear the scars of billions of years of impacts, Enceladus appears to be in constant flux. Its icy skin is young and active, unlike most frozen moons. Cassini's observations also suggest that Enceladus's plumes vary in intensity. At certain points in its orbit, the geysers become more powerful. This suggests tidal forces directly influence the Moon's internal behavior. It is not a random activity, but a highly regulated process governed by interactions with Saturn. The composition of the plumes is another crucial factor. In addition to water and salt, organic compounds including methane and light hydrocarbons have been detected. The combination of these elements with the presence of thermal energy opens the real possibility of microbial life. Although there is no proof, all the fundamental ingredients are there. It is one of the most promising environments for astrobiology beyond Earth. The possibility of life on Enceladus is considered so important that there are proposals to send a dedicated mission to the Moon. The idea would be to land or even drill through the ice in search of biosignatures. But some argue that simply flying through the plumes again, as Cassini did, may be enough to collect material directly from the subsurface ocean. That would reduce the risks and costs of a landing. The thin atmosphere created by the plumes themselves makes direct surface observation difficult, but it also creates a unique microenvironment, with suspended particles in constant motion. This effect feeds back into the rings and maintains a continuous exchange between Enceladus and the space around it. The Moon behaves like a small, self-sustaining hydrothermal machine. Because of its composition and behavior, Enceladus has become a comparison model for icy exoplanets. What we learn there can help identify similar worlds around other stars. The logic is simple. If life can exist beneath ice in our neighborhood, perhaps the same is true in distant systems. This shifts the focus of habitable zone searches. Enceladus's geysers are not just a spectacular phenomenon, they are an active window into the interior of a celestial body. They eliminate the need to dig or drill. One simply has to pass through them at the right time and collect the material expelled. This represents a rare and cost-effective scientific opportunity for space exploration. By studying the thermal properties of Enceladus, we also advance our understanding of internal processes in icy moons. This helps build more accurate models of subsurface ocean formation, heat transfer, and gravitational equilibrium. This knowledge has applications in planetary engineering and future colonization missions. Enceladus is small, icy, and distant. But by observing its water jets, we are, in practice, watching a hidden ocean in action. And perhaps with a few more missions, we will see what lives in it. Until then, it continues to feed an entire ring with its own liquid heart.
A fixed point in space where the gravity of Jupiter and the Sun create traps where asteroids remain captured for billions of years. Gravity is often understood as a direct attractive force, but in space, its geometry creates true dynamic structures. The so-called Lagrange points are regions where the gravitational force of two bodies balances in a stable way. Between Jupiter and the Sun, two of these points, L4 and L5, form zones in which asteroids remain parked for billions of years. These bodies are known as Trojan asteroids. They do not orbit Jupiter directly, but share its solar orbit with precision. The reason they remain stable is mathematical. The gravitational forces of Jupiter and the Sun, combined with orbital motion, create zones of dynamic equilibrium. It's like being in a web of forces that partially cancel each other out. An object that enters these points with the right velocity can remain there virtually forever. This makes these points true gravitational archives of the solar system's past. The number of known Trojans rose from 1,000 in the 2000s to over 12,000 today. Advances in telescopes and orbital simulations have allowed for the discovery of more and more of these hidden bodies. They are not gathered at a single exact point, but in broad regions that extend around the L4 and L5 points. The orbits are not perfectly circular, but the objects oscillate around the point with stability.
Some Trojan asteroids have highly inclined orbits relative to the ecliptic plane. This suggests they were captured during periods of gravitational instability, possibly during the initial migration of the giant planets. Others appear to come from the same origin, sharing similar spectral composition. Studying this population can reveal how the current architecture of the solar system was shaped. In addition to Jupiter's Trojans, other planets also have their own stable asteroids. Neptune hosts the second-largest known group. Even Mars and Earth have a few Trojans. In Earth's case, one of them, 2010 TK7, was identified orbiting Earth's L4 point in an elongated trajectory. It remains there relatively stably despite gravitational disturbances from the Moon and other planets. NASA's Lucy mission was launched in 2021 with the goal of closely studying these asteroids. It will fly by 7 Trojans in Jupiter's 2 main points. The choice of targets was based on diversity. Some are dark and primitive, others appear to have undergone collisions. This sampling will help us understand not only the composition, but also the dynamic history of the region. The composition of these asteroids is varied. Many are rich in carbon, similar to bodies in the asteroid belt. Others exhibit characteristics reminiscent of Kuiper belt objects. This indicates that Trojans may be a mix of bodies from different origins, captured and stabilized during a chaotic moment in the early solar system. The stability of Lagrange points is so great that they are already used as cosmic parking spots for space missions. The James Webb Telescope, for example, is positioned at Earth's L2 point. Although this point is unstable, it allows the telescope to remain in a constant line relative to Earth and the Sun. This maximizes energy efficiency and field of view. In the cases of Jupiter's L4 and L5, the stability is natural. Bodies in these points experience little interference from other forces and can maintain their position even with small disturbances. This property has been confirmed through numerical simulations over decades. Today, these points are studied with interest by both scientists and space engineers. The theory that explains these points comes from the 18th century, developed by Joseph Louis Lagrange. He mathematically predicted the existence of 5 points in any two-body system with a large mass difference. Points L1, L2, and L3 are unstable, but L4 and L5 offer natural equilibrium. The later observation of asteroids confirmed the validity of his theory. In addition to harboring asteroids, L4 and L5 are also safe regions to install future bases or long-term satellites. The absence of large gravitational variations allows fuel savings for orbital corrections. This makes these locations viable candidates for high-precision astronomical observatories or as support points for interplanetary missions. In the future, these orbital warehouses may even be explored for mining. If the composition of some Trojans is rich in rare metals, they could become strategic sources. The stable location facilitates logistic planning and reduces operational risks. What is today an astronomical puzzle may become an economic opportunity. An object that takes 11,000 years to complete one orbit around the Sun. Sedna is one of the most distant objects ever found orbiting the Sun, with an orbital period of over 11,000 years. This means that since the beginning of agriculture on Earth, it has not yet completed a single full cycle. Its orbit is extremely elliptical, taking it to distances where the Sun appears only as a bright star. Discovered in 2003, Sedna challenges classical models of the solar system. The closest point of Sedna's orbit still places it far beyond Neptune. Its farthest point extends to the inner edge of the Oort Cloud. This means it transitions between the known and unknown regions of the solar system. For most of its existence, Sedna remains in near total darkness, far from the Sun's direct influence. It lives in a state of near cosmic exile. The origin of Sedna is one of modern astronomy's greatest mysteries. Its orbit cannot be explained solely by the influence of the known planets. Some scientists believe it was pulled by a star that passed near the Sun during the early formation of the solar system. Others propose it as evidence of an undiscovered planet, the hypothetical Planet 9. Because it is so distant, Sedna has never been visited by a probe. Everything we know comes from telescopic observations and orbital simulations. Even so, its albedo, that is, its ability to reflect light, suggests a relatively bright surface for such a remote body. This may indicate the presence of ice or frozen organic compounds. Its exact composition remains uncertain. Sedna's orbit is so long that humans have never witnessed it completing a full revolution. All accumulated knowledge about it comes from a tiny fraction of its orbital path. Still, based on its position and velocity, it's possible to estimate the shape and duration of its orbit with good precision. It's an example of how mathematics anticipates what the eyes cannot see. Besides being an astronomical curiosity, Sedna is a natural marker of the solar system's extent. It helps define the boundaries of the heliosphere and the Sun's gravitational influence. In a sense, it represents the functional frontier between the solar system and interstellar space. Studying its trajectory helps us understand where the solar territory ends. Sedna's presence also reopens discussions about what defines a planet. Although it is not large enough to be officially classified as a dwarf planet, it shares many characteristics with other members of that category. Its orbit, however, places it in a separate class. It fits neither the patterns of the Kuiper belt nor the Oort cloud, and thus continues to puzzle astronomers. The existence of Sedna has motivated the search for other objects with similar orbits. Some have already been found, with very long orbital periods and highly inclined trajectories. The distribution of these bodies suggests an external gravitational influence acting upon them. This strengthens the hypothesis of a ninth, still unseen planet in a very distant orbit. Sedna also draws attention due to its isolation. It does not belong to any known orbital family. There are no groupings of objects with identical characteristics. This uniqueness makes it even more valuable as an object of study. Every piece of data collected about Sedna could be a unique clue about the processes that shaped the outer edges of the solar system. During its closest approach to the Sun, Sedna may undergo surface changes. Exposure to solar radiation could cause the sublimation of volatile compounds. This may alter its color, texture, or even create a temporary, tenuous atmosphere. Observing these changes would require extremely sensitive instruments, but the event will occur only millennia from now. Sedna's orbit time is so long that it could serve as a geologic reference for the solar system. Its existence preserves the dynamic conditions of an extremely remote past. Instead of being a transient planet, it is like a capsule slowly crossing cosmic time. And every time it appears, it brings with it questions that science is still far from answering. The Martian moon that is slowly falling. Phobos is the larger of Mars's two moons, but it's still small, only 22 kilometers in diameter. Its orbit is extremely close to the planet, just 6,000 kilometers from the surface, closer than any other moon in the solar system. This has an inevitable consequence. Phobos is falling. Every century, it moves about 2 meters closer to the red planet. Unlike most moons that drift away from their planets over time, Phobos is caught in a downward spiral. The cause lies in tidal forces between it and Mars. Since it orbits faster than Mars rotates, it steals angular momentum from the planet and accelerates its own descent. Over time, this dance will bring it to the limit of gravitational breakup. This fate is not a vague guess, it's a mathematical prediction based on long-term measurements. In approximately 30 to 50 million years, Phobos will be so close that it will be torn apart by tidal forces. When this happens, its fragments will likely form a ring around Mars. A planet that today has no rings may have them in the future. Phobos's surface already shows signs of the stress it is undergoing. It is marked by long grooves and ridges, which are believed to be caused by tidal forces stretching it. These features are like cracks in a structure being slowly compressed from within. They weren't formed by impacts, but by gravity in continuous action. Phobos has an uncertain origin. Some theories suggest it is a captured asteroid due to its irregular shape and dark composition. Other hypotheses point to an origin from debris ejected from Mars after an impact. The question remains open. Whatever its origin, its end is already mapped out. Future missions are interested in Phobos for multiple reasons. It could serve as an intermediate base for Mars exploration due to its low orbit. In addition, its surface may hold information about Mars's early environment, as debris from the planet may have settled there. The Japanese MMX mission aims to land on it and collect samples by the end of the decade. Due to its very weak gravity, Phobos cannot retain an atmosphere or sustain geological activity. Even so, it interacts constantly with Mars. Fragments breaking off from its surface may fall onto the planet, and there are records of Martian craters caused by such impact. This subtle exchange makes Phobos an active component of the Martian system. Phobos's fast orbit is remarkable. It completes a revolution around Mars in just 7 hours and 39 minutes. This means that, to an observer on Mars, Phobos rises in the west and sets in the east, the opposite of what we're used to. What's more, it appears 2 or even 3 times per Martian day as a constant, swift presence in the sky. Despite its tiny size, Phobos has a prominent crater named Stickney. About 9 kilometers in diameter, it takes up nearly half the Moon. It is believed that the impact that created it nearly destroyed the body completely. Its edges are deformed and partially collapsed, showing how fragile its internal structure is. Phobos has low density, which indicates it may be a pile of rock and dust held together by weak gravity. It could have large internal cavities or be partially porous. This makes it an unstable object, vulnerable to orbital changes. Its collapse, when it comes, will not be explosive, but gradual and dispersed. Studying Phobos's fall also helps us understand the behavior of other close-in moons in other planetary systems. The mechanics involved are universal. Models based on its orbit help predict the evolution of exomoons around giant planets. In this sense, Phobos is a functional miniature of larger-scale processes. As it orbits and approaches its end, Phobos also challenges models of orbital stability. Its current existence is a delicate balance between gravitational pull and internal resistance. The fall is too slow to be seen in real time, but fast enough to be clearly underway. It's a reminder that even the smallest celestial bodies are in continuous transformation. Jupiter's moon Europa, with a subsurface ocean and constant geological activity, Europa is one of Jupiter's largest moons, with just over 3,000 kilometers in diameter, smaller than Earth's moon, but far more intriguing. The most striking feature of Europa is its bright, almost crater-free icy crust. This smooth and clean surface is a sign of frequent renewal. and beneath it lies a global ocean of liquid water. The existence of this ocean was first suggested by images from the Galileo spacecraft in the 1990s. Visible fractures and cracks indicated internal movement. Later, magnetic data revealed electrical conductivity consistent with salty water beneath the ice. This confirmed that Europa harbors a global ocean with more water than all of Earth's oceans combined. The source of the heat keeping this water liquid lies in gravitational interaction with Jupiter. The immense tidal forces flex the Moon's interior in constant cycles. This process generates frictional heat, enough to prevent complete freezing. Europa is therefore active internally, even without visible surface volcanoes. This internal activity produces observable effects. The surface displays lines, cracks, and regions where large blocks appear to have floated and reorganized. This suggests that the ice is being pushed upward from below, with mobile layers similar to tectonic plates. It's a rare example of geodynamics on a frozen moon. The absence of mountains and presence of flat regions suggest that the ice is relatively thin in some areas. In certain spots, the thickness may be only a few kilometers. This makes it theoretically possible to drill or melt through the ice to reach the ocean. Future missions are already planning to do just that. In addition to water, Europa also shows signs of vapor plumes escaping through fissures. Although not as visible as those on Enceladus, these emissions have been recorded by space telescopes like Hubble. If confirmed, they represent an opportunity to sample the ocean without drilling through the crust, simply by flying through and collecting suspended material. Europa's water is likely salty, containing elements such as sodium chloride and magnesium. This has been inferred from spectral surface analysis and the Moon's magnetic influence. These salts, combined with thermal energy and possible contact with rock at the core, create an environment favorable to complex chemical reactions. Interest in the Moon goes beyond geology. Europa is one of the top candidates for microbial life in the solar system. If organisms exist in its seas, they might live near hydrothermal vents, like extremophiles on Earth. This would not only expand our understanding of life, but also demand a new approach to astrobiology. NASA's Europa Clipper mission is scheduled for launch in the coming years. It will orbit Jupiter and conduct multiple flybys of Europa. Onboard instruments will map the crust thickness, ocean depth, and plume composition. It will be the first detailed investigation of the Moon since Galileo. Europa's icy ground also displays reddish stains, whose origin is still debated. Some theories suggest they are salt or organic compound deposits. Others point to intense radiation that alters the surface's chemical materials. Whatever the cause, these features offer clues about the interaction between the ocean and space. Surface temperatures are extreme, with averages below -160 degrees Celsius. But the thermal stability beneath the crust creates a relatively constant liquid environment. This makes Europa's ocean a stable setting for millions, perhaps billions of years. And where there is stability, there is time for complex processes to unfold. The comet that releases organic compounds and may hold clues to the origin of life. In 2014, the European Space Agency's Rosetta mission arrived at comet 67P Churyumov-Gerasimenko. It was the first time a spacecraft orbited a comet and deployed a lander, Philae, onto its surface. What Rosetta discovered was unexpected. The comet was releasing not just water vapor and carbon dioxide, but also complex organic molecules. These included amino acid precursors and carbon-based compounds essential for life.
The implications were immediate and far-reaching. The presence of these compounds supports the panspermia hypothesis, which suggests that the building blocks of life may have been delivered to Earth by comets or asteroids. Before Rosetta, organic molecules had been detected in space, but this was the first time they were directly sampled from a comet's coma. It proved that comets aren't just dirty snowballs, they're chemically active and rich in prebiotic ingredients. That realization redefined how we view them. Comet 67P releases its materials as it approaches the Sun when solar radiation heats its surface. The heat causes ices to sublimate, ejecting gas and dust into space in large jets. These plumes form the comet's coma and tail and contain volatile molecules stored since the formation of the solar system. Studying them is like opening a frozen time capsule. The material hasn't changed much in 4.6 billion years. The comet's shape also caught scientists off guard. It has two lobes connected by a thinner neck resembling a rubber duck. This odd form suggests it may have been formed by a gentle collision between two smaller bodies early in solar system history. Studying how such structures survive and evolve informs our understanding of early planetary formation. The surface was more rugged and fractured than expected. Rosetta detected formaldehyde, hydrogen cyanide, methanol, and sulfur-containing organics, molecules relevant to biochemical processes. These are not life, but they are ingredients from which life can arise under the right conditions. It strengthened the idea that comets may have, quote, seeded early Earth with critical materials. The early Earth environment may have simply assembled what space delivered. Philae, the lander, bounced after touchdown and ended up in a shaded area, limiting its battery life. Even so, it collected data on the comet's surface composition, density, and magnetism. It found that the comet's outer crust was harder than ice, composed of frozen dust and complex organics. The mission ended contact in 2016, but its data is still being analyzed today. The results keep raising new questions. Not all comets are alike. 67P is a Jupiter family comet, originating from the Kuiper belt and influenced by Jupiter's gravity. Others, like long-period comets, come from the Oort Cloud and contain even more pristine material. If one comet has these organics, many likely do. That opens the door to systematic chemical mapping of comets in future missions. Understanding these compounds also helps define biosignatures to look for in exoplanet atmospheres. Knowing what is naturally produced in space without biology tells us what not to confuse with signs of life. In this sense, comets act as laboratories for distinguishing between abiotic and biotic chemistry. Their simplicity provides clarity that planetary atmospheres do not. The Rosetta mission also provided insight into comet activity cycles. Jets are not constant, but vary depending on orientation, surface composition, and distance to the Sun. The comet wakes up as it approaches, releases gas in bursts, and settles down again after perihelion. Understanding this rhythm improves prediction models, especially for near-Earth comets. Future missions like ESA's Comet Interceptor and NASA's Caesar aim to expand on Rosetta's legacy. These missions will target either a fresh comet or even return a sample to Earth. If successful, they could bring pristine organic material directly into terrestrial labs. That would remove observational uncertainty and open a new phase of prebiotic chemistry studies. Comet 67P is not heading toward Earth, but its relevance isn't about impact risk, it's about what it carries. The fact that ancient drifting ice can contain ingredients for life changes our view of habitability. Life may not be a cosmic accident, it may be a byproduct of chemistry repeated in many places. Rosetta's success showed that comets are not lifeless relics, but active, chemically rich travelers. Their tails aren't just pretty phenomena, they're evidence of dynamic reactions from frozen time. What was once poetic now has data.
and what was once speculative now informs the search for life's origins.
The asteroid Bennu, which could collide with Earth in the future and is already being monitored by NASA. Bennu is a near-Earth asteroid about 500 meters wide, classified as a potentially hazardous object. It has a small but non-zero chance of colliding with Earth in the late 22nd century. NASA has closely monitored its orbit for decades. The probability of impact on a specific date, September 24, 2082, is estimated at 1 in 2,700. That's high enough to warrant serious study. To understand Bennu better, NASA launched the OSIRIS-REx mission in 2016. It reached the asteroid in 2018 and orbited it for over 2 years. In 2020, it performed a touch-and-go sample collection, grabbing surface material and storing it in a capsule. That sample returned to Earth in September 2023, the first time NASA has retrieved material from an asteroid. Bennu's surface turned out to be more chaotic than expected. Instead of firm regolith, it was covered in loose rubble with rocks that seemed to float in extremely low gravity. When the spacecraft touched down, it sank into the surface before pushing off. This revealed a surface with little cohesion, like a cosmic pile of gravel. Analysis of the return samples is ongoing, but early results confirm that Bennu contains organic molecules and hydrated minerals. These point to past interaction with water, likely when Bennu was part of a larger parent body that underwent aqueous alteration. These findings provide insights into the conditions that existed in the early solar system. Bennu belongs to the carbonaceous B-type asteroids, thought to be among the most primitive objects in the solar system. They formed in the outer regions where sunlight was scarce and icy materials were abundant. Studying them is like peering into the initial chemical inventory of the planets. Bennu may carry signatures of ancient solar system processes. Its orbit is influenced by a subtle but critical phenomenon called the Yarkovsky effect. This occurs when an asteroid absorbs sunlight and re-emits it as heat, creating a tiny but continuous thrust. Over decades, this effect alters Bennu's trajectory. Accurate modeling of this force is essential to predicting future impacts and planetary defense strategies. Time is the most powerful tool in planetary defense. Bennu's relative proximity also makes it a test case for deflection technologies. Concepts like kinetic impactors, gravity tractors, and even laser ablation have been discussed in context with this asteroid. It's not a doomsday object, but it's the ideal real-world rehearsal for what such a threat might look like. The return of the OSIRIS-REx sample marks a turning point. For the first time, we have physical access to a potentially hazardous asteroid's surface. The knowledge it provides could help us build the first effective planetary shield, not for today, but for centuries ahead. It's a rare example of true intergenerational science. Bennu is quiet now, just another rock drifting through space. But it's the kind of object that changed Earth's history before, and might again someday. Studying it isn't just academic, it's how we ensure we'll be ready next time.
Hi, how are you? Are you still awake? Sorry for interrupting your relaxation. I just wanted to thank you for watching our video and let you know that we're trying to hit our subscriber goal by the end of this month. We've noticed that many of our viewers still haven't subscribed to our channel, so I'd like to ask you, grab your phone and look up the Sleep Fact channel, or point your camera at the QR code here and hit subscribe. Now, let's continue with the video.
The Oort Cloud, a field of comets that could unleash destruction on Earth at any moment. The Oort Cloud is a theoretical structure composed of trillions of icy objects surrounding the solar system. Unlike the Kuiper Belt, which lies just beyond Neptune, the Oort Cloud is much farther away, between 2,000 and 100,000 astronomical units from the Sun. This means its objects are literally at the edge of the Sun's gravitational field. They form a giant, encompassing, and invisible sphere.
No object has ever been directly observed in this region, but the existence of the Oort cloud is inferred from the behavior of long-period comets. These comets appear from all directions in the sky, suggesting a spherical rather than planar origin. When disturbed by external forces, these bodies are sent toward the Sun, sometimes crossing Earth's orbit. The disturbances that trigger these trajectories can be small. A star passing tens of thousands of astronomical units away can alter the local gravity. The galaxy itself, with its gravitational field and galactic tides, also influences the stability of Oort cloud objects. Any of these events can awaken dormant comets. Comets originating from the Oort cloud are considered dangerous because they come from great distances and move very fast. Their approach time is short, and their trajectories are often only detected weeks before perihelion. Since some are dozens of kilometers in diameter, an impact would be catastrophic. Comet Hale-Bopp, for instance, came from this region and had a nucleus over 60 kilometers wide. The cloud is theoretically divided into two parts, an inner region called the Hills cloud and an outer, more diffuse region. The inner part would be denser and contain most of the objects. The outer part is more susceptible to interstellar influences. This layered structure helps explain why some comets have nearly parabolic orbits, while others have more regular elliptical paths. It is believed that the Oort cloud is a remnant of the solar system's formation. During the first few million years, interactions with Jupiter and the other gas giants flung millions of bodies to the outer regions. Some were ejected from the system, others became trapped, orbiting at immense distances. The cloud is therefore a kind of primordial frozen graveyard. Despite being so far away, the Oort cloud has direct relevance to Earth. It's estimated that catastrophic impacts in the past, like the one that caused the extinction of the dinosaurs, may have originated from long-period comets. These events are rare, but the potential damage is extreme. For this reason, monitoring deep space has become a priority for planetary defense. One of the challenges is that these comets don't follow predictable patterns like near-Earth asteroids. They can spend millions of years in stable orbits and suddenly be deflected. Early detection is difficult because they are small, dark, and reflect little light until they approach the Sun. This gives little time to respond if one is on a collision course. Future missions like the Vera Rubin Observatory aim to enhance our ability to detect deep sky objects. Its wide-field telescope will be able to observe subtle changes over short timescales. The expectation is to detect long-period comets weeks or even months in advance, a crucial improvement for planetary defense. The Oort cloud also raises questions about the true boundaries of the solar system. How far does the Sun's influence reach? Where does interstellar space begin? Objects like Sedna and others with extreme orbits appear to form a link between the inner system and this outer region. They may be indirect messengers of activity in the Oort cloud. If a comet from the cloud enters a collision course with Earth, the defense options are limited. Techniques like kinetic missiles or gravitational deflection only work with prior planning. With little warning time, the impact would be inevitable. That's why mapping this region has become a scientific priority with direct consequences for the future of civilization. The Oort cloud is not just a space frontier, it is an unstable reservoir of destructive potential. Every new comet that appears might be a harmless visitor or a reminder that deep space still harbors real and unpredictable dangers. The dwarf planet Haumea, spinning so fast it seems on the verge of breaking apart. Haumea is a dwarf planet located in the Kuiper belt beyond Neptune. It is known for its extremely elongated, ellipsoidal shape, making it resemble a rugby ball more than a spherical celestial body. This shape is a consequence of its incredibly fast rotation, completing one full turn in just 3.9 hours. No other large object in the solar system spins this quickly. This rotation causes Haumea to flatten at the poles and stretch at the equator. Its gravity is not strong enough to pull it back into a spherical shape. This places it at the edge of structural stability. Any faster rotation, and it would begin to break apart. It's a delicate balance between internal cohesion and centrifugal force. Haumea is not only fast, it's also compositionally peculiar. Its surface is covered with crystalline water ice, which is unusual for such distant objects. This indicates it has undergone internal heating or collisions that exposed deeper layers. The pure ice reflects a lot of light, making Haumea brighter than other similarly sized bodies. Another remarkable fact, Haumea has two natural satellites, Hiaka and Namaka, both likely formed after a giant collision, which may have also caused its extreme rotation. The presence of these moons combined with the fresh ice supports the theory of a catastrophic impact. Haumea may be the remnant of a larger body that was shattered and reassembled. In 2017, astronomers detected something even more surprising. Haumea has a ring. It was the first known dwarf planet with such a structure. The ring orbits in a plane aligned with Haumea's equator, exactly where the rotational effects are most intense. This ring may be the result of debris ejected after impacts or gravitational instabilities. The presence of a ring around such a small body challenges classical models about where and how rings form. Until then, rings were associated only with giant planets. The discovery around Haumea forced astronomers to revise theories about the formation and persistence of rings in smaller bodies. The dynamics involved depend on fast rotation and a fine balance of local forces. Haumea is also part of a dynamic family, a group of objects with similar orbits and compositions. This group is rare in the Kuiper belt and reinforces the idea that all these bodies emerged from a common fragmentation event. Studying them allows scientists to reconstruct the history of collisions that occurred at the edges of the solar system. Haumea's density is relatively high, suggesting a rocky core surrounded by a layer of ice. This structure is similar to that of some of Jupiter's and Saturn's icy moons. However, its unusual shape makes it unique among dwarf planets. Even other objects, like Eris, Makemake, or Pluto, do not share this combination of rotation, shape, and ring. Haumea also shows variations in brightness as it rotates. This happens because of its elongated shape and differing albedo across its surface. With each rotation, it reflects more or less light, creating a cyclical pattern. This behavior was essential to calculate its rotation speed, even before detailed images were available. Being located in the Kuiper belt, Haumea is too distant for current mission capabilities. No probe has visited it, and all we know comes from ground and space-based telescopes. Even so, it plays a central role in the study of trans-Neptunian objects. Its existence shows that the morphological and dynamic diversity at the edge of the solar system is greater than previously imagined. Haumea's extreme rotation even influences the stability of its ring. If it spun more slowly, the ring would likely disperse. If it spun more quickly, the dwarf planet itself could start losing mass. It lives in a delicate balance between centrifugal forces and gravitational cohesion. It is an object that tests the limits of what is physically possible. Among dwarf planets, Haumea is the one that most defies simple classification. Its shape, rotation, moons, and ring form a unique set. It is not just a distant point of light, it is a miniature dynamic system, spinning at the edge of stability.
The asteroid 16 Psyche, almost entirely made of metal and worth trillions of dollars. 16 Psyche is one of the most unusual objects in the asteroid belt, a massive body thought to be composed mostly of metal rather than rock or ice. Measuring around 226 kilometers across, it is one of the largest asteroids known. What makes Psyche unique is that it may be the exposed core of a failed planet, a remnant from the early days of the solar system. If confirmed, it would be the only metallic core we can directly study. That alone gives it enormous scientific value. Spectroscopic analysis suggests Psyche is made largely of nickel and iron, much like Earth's own inner core. This composition hints that Psyche could have once been part of a protoplanet, whose outer layers were stripped away by violent collisions. Its density, reflectivity, and radar properties all point to a metallic interior, though recent studies show it may also contain silicates and sulfur-rich minerals. It is more complex than initially thought. Because of its unusual makeup, 16 Psyche has been called a metal world. Theoretical calculations estimate its raw material could be worth over 10 quadrillion USD at current market prices. Of course, mining Psyche is not feasible yet. Still, its sheer potential draws attention not only from planetary scientists, but from economists and futurists speculating on the future of space resource extraction. NASA is currently preparing a mission to Psyche, a spacecraft of the same name. The Psyche mission launched in October 2023 and will arrive in 2029. Once in orbit, it will spend 21 months mapping the surface, analyzing its composition, and studying its magnetic field. It will be the first time a spacecraft visits a metallic world. What we learn there could redefine planetary formation models. One of the big questions the mission seeks to answer is, how do planets develop differentiated cores? Psyche offers a rare chance to observe a core without needing to drill through crust or mantle. If Psyche truly is a core, it may show features like metallic ridges, magnetic remnants, or impact scars frozen in time. If it's not, its makeup still challenges assumptions about asteroid formation. Psyche doesn't have the jagged shape of smaller asteroids. Radar imaging suggests it has a somewhat spherical shape, with flattened regions likely formed by collisions. Some features may be craters or depressions formed by slow deformation. Its surface may contain areas of solid metal, loose metallic gravel, or mixtures of rock and metal, each with different origins and mechanical behaviors. Magnetic studies from Earth hint that Psyche may still carry traces of a magnetic field, a fossil of ancient planetary activity. If this is confirmed by the spacecraft, it would be the first magnetic remnant found on an asteroid. This could help understand how small bodies generate and lose magnetic fields, something still not fully explained in planetary science. Another aspect of interest is the absence of any known moons or ring systems. For an object of its size, this is rare. It suggests Psyche is relatively isolated and perhaps dynamically stable. If it ever had satellites, they may have been lost during collisions or destabilized by its unique mass distribution, or it may simply have formed differently from other large asteroids. 16 Psyche is not considered a threat to Earth. It orbits between Mars and Jupiter and remains well outside the zone of potentially hazardous objects. But what it teaches us could influence how we handle metallic near-Earth asteroids in the future, for defense, science, or resource use. Understanding how metal behaves in space conditions will be vital in those contexts. Its surface could also act as a test bed for robotic mining systems or future autonomous navigation.
If a metallic surface behaves differently under sunlight or micro-impacts, it could affect the design of landers and drills. NASA's mission will not land, but high-resolution mapping will offer the next best thing. This will guide future exploration technologies. The metal-rich nature of Psyche also informs theories about the early solar system's violent past. If it was once part of a larger body, its exposure means a massive collision occurred, strong enough to destroy a world. That collision may have created other fragments still orbiting the Sun today. Psyche is the survivor, still carrying the record of that ancient impact. Whether it's a stripped core or something entirely different, Psyche is a natural archive of metal under space conditions. It's a place where planetary science, material science, and space economy all meet. In studying it, we touch the heart of a planet that never was, and maybe glimpse the future of space industry.
The dwarf planet with rings wider than Saturn's, but almost invisible. Chariklo is not a planet, not a moon, and not an asteroid in the classical sense. It's a centaur object, a small body that orbits between Saturn and Uranus, part rock, part ice, and highly dynamic. In 2014, astronomers made a shocking discovery. Chariklo has rings, and not just narrow traces, they are structured, distinct, and remarkably wide for such a small object. At only 250 kilometers in diameter, Chariklo is the smallest known body with a ring system. The rings were detected during a stellar occultation, when Chariklo passed in front of a distant star. Instead of a single blink, the star's light dimmed multiple times before and after the main event. This meant something was blocking the light on both sides, two narrow, dense rings orbiting Chariklo. It was the first time such a feature had ever been seen on an object so small. The inner ring is about 7 kilometers wide, and the outer one roughly 3 kilometers. They're separated by a narrow gap, similar to the structure seen in the rings of Saturn or Uranus. The origin of the rings is still uncertain. One theory suggests they formed after a collision or fragmentation event, possibly ejecting debris into orbit. The rings have remained stable over time, an unexpected result. Because Chariklo is so small, its rings are not visible through standard telescopes. They don't reflect much light and are often missed in large-scale surveys. Only precise alignment during occultation events reveals them. This means there could be more ringed small bodies in the solar system, simply undetected due to observational limitations. Chariklo opened a new frontier. The material in the rings is likely composed of water ice and dust, similar to other ring systems. But due to Chariklo's weak gravity, the particles behave differently. There's a constant push and pull between coalescing into moons and dispersing into space. The balance they maintain suggests some kind of shepherding, either from unseen moonlets or orbital resonances. This discovery challenged long-held assumptions that rings only occur around gas giants. In fact, it redefined what scientists thought small bodies were capable of. It also sparked interest in revisiting data from other centaurs, like Chiron, which may have similar features. After Chariklo, rings became a new category of small body behavior worth investigating. Observations suggest the rings could cast shadows on Chariklo's surface, depending on the angle of sunlight. These seasonal effects may subtly alter surface temperature or brightness. Long-term monitoring could reveal how the rings interact with the central body. They are not just decorative, they influence the object's environment in measurable ways. Chariklo's rotation period is about 7 hours, and the rings orbit closely around its equator. That alignment suggests a long-term gravitational equilibrium, similar to Saturn's ring system. It's a kind of microcosmic version of the dynamic seen in much larger planetary systems. Studying this miniature case offers insight into ring stability in low-gravity environments. No mission has visited Chariklo, but it remains a high-interest target for future flybys.
Its size, location, and dynamic features make it an ideal candidate for studying collisional remnants and ring dynamics. A close-up look could reveal whether it has moonlets, how the ring particles behave, and what their composition truly is. Other centaurs may harbor rings as well. Chiron, another centaur, has shown signs of similar dimming events. If confirmed, this would imply that ring systems are more common among small bodies than previously thought. That would force scientists to revise models of small body evolution and ring formation. The rings may also offer clues to Chariklo's internal structure. If they were created by a collision, their properties reflect the makeup of Chariklo itself. Icy debris, cohesive clumping, or high reflectivity could all suggest a layered or porous core. Each trait adds to the puzzle of how such small bodies survive and evolve in the chaotic outer solar system. Chariklo is not bright or massive. It doesn't command attention until you notice the rings. Then it becomes a cosmic anomaly, a tiny world mimicking the grandeur of giants.
Triton, the moon that orbits Neptune backward, as if it were captured by force. Triton is Neptune's largest moon, and easily its strangest. Unlike most large moons in the solar system, Triton orbits in retrograde motion, meaning it moves in the opposite direction of Neptune's rotation. This alone strongly suggests that Triton was not formed around Neptune, but rather captured later. It's a gravitational outsider, locked into orbit by a violent past. The retrograde orbit is extremely rare for large moons and poses a puzzle. How was Triton captured without being destroyed? The most accepted theory is that Triton was once part of a binary system, orbiting another object. When this system passed too close to Neptune, gravitational forces tore it apart. Triton was captured, and its partner was ejected into space. Triton's orbit is also highly inclined, tilted compared to Neptune's equator. Over millions of years, tidal interactions have circularized its path, but that tilt remains. These orbital traits mean Triton is slowly spiraling inward. It will eventually either crash into Neptune or break apart, possibly forming rings. This moon is on a very long countdown to destruction. It's also geologically active. Triton has geysers, dark plumes of material spewing from its surface, discovered by Voyager 2 in 1989. These are likely powered by cryovolcanism, where liquid nitrogen or volatile ices erupt through the crust. This activity is unusual for a moon so far from the Sun, and it suggests a subsurface energy source is still active today. The surface of Triton is one of the coldest in the solar system, averaging -235 degrees Celsius. Despite this, it shows evidence of terrain renewal. It has few impact craters, meaning the surface is relatively young. It features smooth plains, ridges, frozen lakes, and oddly shaped depressions. These point to an internal mechanism still shaping the surface. Triton may have a subsurface ocean, though this hasn't been confirmed. The internal heat could come from the tidal forces induced by its capture and subsequent orbital adjustments. If such an ocean exists, it would be another candidate for possible life beyond Earth, albeit a remote and extreme one, but for now that remains theoretical. Its atmosphere, although thin, consists mostly of nitrogen with traces of methane. This thin layer likely originates from surface sublimation during Neptune's seasonal changes. It's enough to drive surface winds and transport particles. This atmosphere is unlike any other in the outer solar system, and it behaves more like a seasonal skin than a permanent envelope. Triton's surface also reflects a large amount of sunlight, making it unusually bright. Much of this is due to the deposition of nitrogen frost, creating a pale, icy shell. Beneath that shell are darker materials exposed by geysers and potential cryovolcanic activity. This contrast gives Triton a mottled appearance when seen from orbit.
Voyager 2 remains the only spacecraft to have visited Triton, and only during a brief flyby. Despite the short encounter, it revealed a complex and evolving world, completely unexpected at the time. Triton stood out in the data, raising more questions than answers. Since then, no missions have returned to it. Triton's retrograde orbit means it was likely a dwarf planet, similar to Pluto, before its capture. If true, it would make Triton the only known Kuiper Belt object brought into orbit around a planet. This crossover between regions of the solar system is rare, and Triton is living proof of planetary migration and chaotic gravity. The capture of Triton likely disrupted Neptune's existing satellite system. Any native moons that orbited in the normal direction may have been flung out or destroyed. Today, Triton dominates Neptune's moon system in size and mass. Its presence rewrote the dynamics of Neptune's orbiting bodies. If humanity ever sends a probe to Neptune, Triton will be the main scientific target. It's a frozen enigma, part Kuiper Belt remnant, part active world, part orbital anomaly. Its past was stolen, its future is doomed, and its present is still full of motion. Enceladus, the moon that shoots water with organic molecules from its frozen interior. Enceladus is a small moon orbiting Saturn, but it has become one of the most exciting objects in planetary science. Beneath its icy surface lies a global ocean of liquid water, confirmed by gravitational measurements and analysis of surface features. More than that, Enceladus is actively expelling material from that ocean into space, visible jets of water vapor and ice particles erupting from the South Pole. These jets were discovered by NASA's Cassini spacecraft, which flew through them multiple times. Cassini's instruments detected organic molecules, including carbon dioxide, methane, and even complex hydrocarbons, all essential ingredients for life. It was the first time scientists directly sampled materials from an extraterrestrial ocean without drilling or landing. The source of the jets is a series of fractures known as tiger stripes, long parallel cracks in the ice crust. These fissures appear to connect the subsurface ocean directly to the surface. The material is released at high speed, forming plumes that reach hundreds of kilometers into space. Some of it escapes into orbit, while the rest falls back, coating the surface with fresh ice. This constant resurfacing gives Enceladus its high albedo. It reflects almost all sunlight, making it one of the brightest objects in the solar system. The process also helps maintain Saturn's E-ring, which is composed largely of particles from these jets. Enceladus is essentially feeding an entire planetary ring with material from its interior. The energy source behind the activity is tidal heating. Saturn's gravity exerts regular, rhythmic force on Enceladus, squeezing and stretching it. This generates heat through friction, which keeps the subsurface ocean in a liquid state. The same mechanism powers volcanoes on Jupiter's moon Io, but here it fuels cryovolcanism instead. The internal structure of Enceladus likely includes a rocky core, surrounded by a layer of liquid water, and then the icy crust. This configuration allows for chemical interactions between rock and water, a key ingredient for potential life. Some models suggest hydrothermal vents could exist on the ocean floor, like those on Earth where microbial life thrives. Cassini's flybys revealed not just water and organics, but also salts and silica particles. These are consistent with contact between liquid water and warm rock, further evidence of hydrothermal activity. It means Enceladus has all three key ingredients for life: liquid water, organic chemistry, and energy. That combination makes it a top target in the search for extraterrestrial life. Enceladus is only about 500 kilometers in diameter, yet it outperforms many larger moons in terms of scientific interest. Its small size makes the level of internal activity even more surprising. Unlike Europa, which may have a thick icy shell, Enceladus appears to have accessible pathways between ocean and space. This makes it a natural candidate for future sampling missions. No landers have visited Enceladus yet, but concepts exist. Missions could fly through the plumes and capture particles for return to Earth, or analyze them on site. Because the ocean contents are already being ejected, there's no need to drill. The Moon is doing the hard work for us. All we have to do is intercept it. The plumes vary in intensity depending on Enceladus's position in its orbit. This suggests the cracks open and close slightly with tidal forces, controlling the flow of material. Studying this variation helps refine models of the Moon's internal mechanics. Each eruption is like a pulse, revealing conditions deep below the surface. The material ejected may not just include gases and ice, but also micro or nanometer scale particles, potentially biological in origin. Instruments sensitive enough could detect amino acids, lipids, or other biosignatures. Enceladus might be one of the best chances for finding life in the solar system without even landing. Despite being frozen on the outside, Enceladus is geologically and chemically alive. It's small, hidden in Saturn's shadow, but it may contain answers to one of humanity's oldest questions. In its cold, dark ocean, something could be swimming, and we're already breathing in its chemical trace.
The dwarf planet Sedna, whose massive orbit challenges the existence of a ninth planet. Sedna is a distant, reddish world that resides on the outer edge of the solar system, far beyond the orbit of Neptune. It is classified as a dwarf planet candidate and follows an orbit so vast that it takes approximately 11,400 years to complete one revolution around the Sun. Its discovery in 2003 shocked astronomers. Nothing else known at the time had such an extreme, detached orbit. It quickly became a cosmic mystery. At its closest approach to the Sun, perihelion, Sedna still remains more than 76 AU away, twice as far as Pluto ever gets. At its farthest, aphelion, it stretches out to nearly 1,000 AU. This huge, elongated orbit cannot be easily explained by interactions with known planets. Sedna appears to be gravitationally influenced by something we haven't yet identified. That's where the idea of a Planet 9 begins. The hypothesis suggests that Sedna and other extreme trans-Neptunian objects have been shaped by a massive, unseen planet. This hypothetical body would orbit far beyond Neptune, exerting gravitational influence over time. The theory gained traction as more distant objects with similar orbital alignments were found. These alignments are statistically unlikely without an external force acting on them. Sedna's orbit is stable but strange. It doesn't intersect the paths of any known planets, nor does it interact strongly with the Kuiper belt. It's in a region called the inner Oort Cloud, or detached disk, a transition between familiar solar system objects and the deep, icy unknown. Its orbit is tilted and stretched, indicating it may have been nudged by a massive force long ago. There are a few theories on how Sedna ended up there. One posits a close stellar encounter in the Sun's early history. Another star passed nearby, pulling Sedna outward. Another theory points to the migration of the giant planets, particularly Neptune, stirring up outer solar system bodies. But the most intriguing explanation remains the potential influence of a ninth planet. Sedna itself is about 1,000 kilometers in diameter, likely spherical, and reddish in color due to surface tholins, complex organic compounds created by cosmic radiation.
Its surface is cold and inert, but stable. There are no signs of geological activity, atmospheres, or plumes. It's essentially a preserved relic from the solar system's formation, untouched for billions of years. Because of its great distance, Sedna is invisible to the naked eye and incredibly faint even in powerful telescopes. Its discovery was a product of luck, timing, and patience, and we've likely missed hundreds of similar objects. Each discovery pushes the edge of the known solar system outward. Sedna has redefined where our cosmic backyard ends. Sedna hasn't yet completed even a fraction of its orbit since humans invented agriculture. All our knowledge of it comes from observing a tiny arc of its motion across the sky. Still, astronomers can project its orbit with great precision using gravitational models. What we see now is only a snapshot in its multi-millennial journey. If Planet 9 exists, it may orbit hundreds of billions of kilometers from the Sun, taking 10,000 to 20,000 years to orbit once. Sedna and its neighbors may be markers pointing to its path. Each newly discovered object with an unusual orbit becomes a potential breadcrumb on the trail of this hidden world. That's why Sedna is so scientifically important. Because it's so distant and slow-moving, no mission has been proposed to visit Sedna. With current propulsion technology, a flyby would take decades. Still, it remains under continuous observation. Future telescopes like the Vera C. Rubin Observatory will likely find more Sedna-like objects, and maybe pin down Planet 9's location. Sedna's mere presence changes how we think about the architecture of our solar system. It's not part of the Kuiper Belt, not part of the Oort Cloud, and not linked to any gravitational family. It's a cosmic orphan, possibly one of many. Each raises new questions about the unknown aspects of the Sun's birth environment, migration, and gravitational influence. Sedna doesn't need volcanism or geysers to be fascinating. Its orbit alone holds implications for planetary dynamics, solar system formation, and interstellar interactions. By existing where it does, it asks a quiet but powerful question. What else is out there pulling the strings? The region where time passes more slowly due to the Sun's gravity. According to Einstein's theory of general relativity, gravity doesn't just pull, it also bends space and slows down time. This effect, known as gravitational time dilation, occurs around any massive object. The stronger the gravitational field, the slower time moves. That means that time on Earth flows slightly slower than it does far out in interplanetary space. And near the Sun, it slows even more. The difference is tiny but measurable. Atomic clocks flown aboard satellites or placed at high altitudes run faster than those on Earth's surface. That's because Earth's surface is deeper in its own gravity well. GPS satellites account for this time dilation to provide accurate positioning. Without these corrections, GPS systems would drift by kilometers each day. Around the Sun, the effect is more intense. A clock placed close to the Sun would tick slower than one far away. If two synchronized probes were sent into space, one staying near Earth, another plunging toward the Sun, their clocks would gradually fall out of sync. This isn't just a thought experiment. Missions like Parker Solar Probe must account for this effect in their telemetry. In deep space, far from any major gravitational body, time flows slightly faster. If you lived your entire life in deep interstellar space, you'd age a few nanoseconds more than someone who stayed near Earth. These are incredibly small differences, but in high-precision navigation and physics, they matter. The universe doesn't share time equally. This variation in time affects orbit calculations, especially for satellites around massive bodies. Models must incorporate relativistic corrections to keep them accurate. NASA's Deep Space Network, which communicates with far-flung probes, uses relativistic math to track signals that travel through gravitational fields. Even a microsecond miscalculation can cause long-term errors. The most extreme gravitational time dilation occurs near black holes and neutron stars, but the Sun's effect is enough to study. Its mass bends spacetime enough to delay signals and alter trajectories of spacecraft and light. During solar eclipses, starlight passing near the Sun appears slightly displaced, a phenomenon first confirmed in 1919, verifying Einstein's theory. The concept is also used in time transfer protocols between ground stations and spacecraft. Clocks on Earth are synchronized with those on orbiting craft to account for both gravitational and velocity-based time dilation. These two effects often work in opposite directions, depending on altitude and speed. Balancing them is crucial for communication accuracy. Time dilation around the Sun is a gentle effect, but persistent. For probes venturing close, like ESA's upcoming solar orbiter, tiny adjustments accumulate over time. Flight dynamics teams must predict these shifts with precision. It's a subtle demonstration of how even time itself is curved by the Sun's presence. These effects are not hypothetical. They're embedded in the software of everyday systems. Smartphones that use GPS, spacecraft that perform slingshot maneuvers, and even Earth observation satellites all rely on relativistic models. The Sun's gravity shapes not just paths, but seconds. Interestingly, gravitational time dilation creates an asymmetry across the solar system. Mercury exists in a slightly slower time frame than Pluto. That means a second on Mercury passes marginally slower than one in the Kuiper Belt. Over long timescales, this differential accumulates, though in practice it's imperceptible to humans. In missions involving multiple gravity wells, like slingshots around planets, engineers calculate how both gravity and speed affect onboard clocks. That's because velocity-based time dilation, from special relativity, compounds with gravitational time dilation. Together, they form the complete picture of time in motion. Time is not a fixed background in space. It's a field that bends, shifts, and adapts to the distribution of mass. And the Sun, with its vast gravitational reach, slows time just enough to remind us, even seconds are relative. The dwarf planet Ceres and its unexplained bright spots. Ceres is the largest object in the asteroid belt and the only dwarf planet located in the inner solar system. Roughly 940 kilometers in diameter, it makes up nearly a third of the asteroid belt's total mass. For many years, it was just another distant dot in the sky, until NASA's Dawn spacecraft arrived in 2015. As it approached, cameras revealed something unexpected: bright, white spots on Ceres' otherwise dark surface. The most prominent of these spots was located inside Occator Crater, a massive impact basin about 90 kilometers wide. From orbit, the bright material looked like it had been painted onto the crater floor. As dawn got closer, scientists realized these weren't light reflections or camera errors. The spots were real and baffling. Their brightness far exceeded the surrounding terrain. Spectral analysis suggested the spots were composed primarily of sodium carbonate, a type of salt. But salts like these typically require liquid water to form. That raised a bigger question. How could briny material reach the surface of a cold, rocky dwarf planet? The answer might lie beneath Ceres' crust, where evidence suggests subsurface reservoirs of liquid or slushy water. This possibility became stronger as Dawn mapped variations in gravity over the surface. Subtle fluctuations indicated that the crust was not entirely rigid. Instead, parts of it seemed weak or softened, consistent with an icy, partially liquid subsurface. That would explain how salty fluids might migrate upward through cracks caused by impacts or internal stress. The salt deposits are relatively young, geologically speaking, estimated to be less than 10 million years old. That's recent in solar system terms, implying the process that formed them is still active or occurred not long ago. Ceres may not be entirely dead. It may have been active much more recently than anyone expected. The dwarf planet went from static rock to dynamic world. In addition to salt, some areas contain ammonium-bearing clays, which are rare in the inner solar system. This points to a formation or alteration in a colder environment, perhaps hinting that Ceres formed farther out and migrated inward. Alternatively, it may have incorporated icy materials during its early development, preserving them deep below the surface. Interestingly, the bright areas are also thermally anomalous. Measurements from Dawn's infrared spectrometer showed that these regions retained heat differently than surrounding terrain. This behavior could indicate ongoing outgassing or residual activity, perhaps from slowly evaporating brines. In some ways, Ceres behaves more like a transitional body than a true asteroid or terrestrial planet. Despite being airless, Ceres does have a transient exosphere, a faint, temporary envelope of water vapor. This vapor may originate from sublimating ice or cryovolcanic activity. It's not enough to sustain an atmosphere, but its presence is significant. It proves that the surface is chemically and thermally active, at least in specific regions. Ceres also features cryovolcanic domes, the most prominent being Ahuna Mons, a 4-kilometer-tall mound with smooth slopes. It resembles a small icy volcano and may have erupted salty slush from within. Unlike volcanic features on Earth, cryovolcanoes release fluids that freeze immediately, forming steep, frozen deposits instead of lava flows. These findings position Ceres as one of the few places in the inner solar system where habitability conditions, even if minimal, might exist. A subsurface salty ocean, occasional fluid transport, and protective crust all suggest potential for biochemical processes. While unlikely to host life today, Ceres could teach us about precursors to habitability. Future missions may return to Ceres with landers or sample return technology. Its proximity to Earth and complex geology make it a tempting target. It bridges the gap between icy moons and rocky planets, an in-between world with characteristics of both. Ceres doesn't fit neatly into any category, which is exactly what makes it compelling. The bright spots are no longer unexplained, but their full story is not yet told. They speak of internal processes, fluid migration, and unexpected activity on a world once thought to be inert. Ceres glows not just from salt, but from questions that push planetary science into new territory.
The comet Arrokoth, shaped like two worlds stuck together and preserving secrets from the solar system's birth. Arrokoth, previously nicknamed Ultima Thule, is a contact binary object in the Kuiper Belt, the most primitive region of the solar system. It was visited by NASA's New Horizons spacecraft on January 1, 2019, making it the most distant object ever explored up close. Arrokoth looks like two flattened spheres stuck together, resembling a snowman in space, but its shape hides profound scientific value. This peculiar structure is not accidental. Arrokoth likely formed when two separate planetesimals, small building blocks of planets, slowly merged. The merger occurred at a speed of just a few meters per second, meaning the two bodies gently joined without shattering. That preserved their internal structures and surface characteristics, making Arrokoth a time capsule from over 4 billion years ago. The surface is a uniform reddish color, the result of complex organic molecules called tholins, formed by cosmic radiation acting on simple compounds like methane.
These organics suggest chemical processing over billions of years. They're not biological, but they are potential ingredients in prebiotic chemistry, giving Aerokoth importance in the study of life's origins. Aerokoth's smooth, relatively uncratered surface indicates that it has remained undisturbed since formation. No major impacts, no tidal forces, and no resurfacing events have altered it. That makes it one of the most pristine bodies ever observed. Studying it allows scientists to test models of how early solar system materials clumped together to form planets. Its flattened lobes are surprising. Instead of being spherical or irregular, each segment is pancake-shaped, a trait not fully explained by current models. Their flatness may indicate rotational compression or shape evolution during formation. It suggests that early solar system conditions allowed for delicate accumulation rather than violent collisions. The neck connecting the two lobes is narrow and smooth, indicating that the final merger likely caused surface heating and slight flow of materials. This would have sealed the two bodies together, forming a single object with a shared gravitational identity. It's a natural fusion, untouched since its creation. Aerokoth rotates every 15.9 hours, showing no significant wobble or axial tilt. Its stability adds to the picture of a body that hasn't been perturbed for billions of years. Unlike asteroids or moons bombarded by impacts and tidal stresses, Aerokoth has quietly orbited in the Kuiper Belt, a frozen relic of planetary origins. The environment where Aerokoth resides is extremely cold and sparsely populated. That's part of why it has stayed intact for so long. The Kuiper Belt acts as a preservation zone, allowing fragile objects like this to remain unchanged. It's a natural laboratory of the conditions that existed just after the Sun and planets began forming. Before New Horizons, no spacecraft had ever visited a classical Kuiper Belt object. The mission showed that these distant bodies are not just icy rocks, they're diverse, chemically rich, and structurally complex. Aerokoth proved that planetary formation in the early solar system was gentler and more layered than previously assumed. Spectral data revealed methanol ice on the surface but little water ice, a surprising result. This composition hints at varying conditions in the solar nebula during formation. Methanol also supports the idea that complex organics could be widespread in the outer solar system, formed through long-term cosmic radiation. Aerokoth's orbit is nearly circular and lies within the Kuiper Belt's cold classical population. These objects are believed to have formed where they are, without being scattered by migrating planets. That makes them excellent candidates for studying the unaltered conditions of solar system formation, and why Aerokoth was selected as a target. Aerokoth doesn't shine brightly or dominate its region, but in silence, it tells the story of how worlds begin. It carries the fingerprints of the solar system's earliest structures, gently pressed together and left unchanged for eons. It's not a fossil, it's the raw material of everything we've ever called a planet. Iapetus, the moon that's half bright, half dark, and shaped like a walnut. Iapetus is one of Saturn's more distant moons, orbiting far outside the planet's main ring system. What makes it stand out immediately is its striking two-tone surface. One hemisphere is dark as coal, while the other is bright as snow. This extreme contrast has puzzled scientists since Giovanni Cassini first noticed it in 1671. It remains one of the most unusual surface features in the solar system. The dark region, known as Cassini Regio, absorbs much more sunlight than the rest of the moon. In contrast, the bright terrain, composed largely of water ice, reflects most of the sunlight. This difference creates temperature variations that are thought to drive surface changes over time. The warm, dark regions promote sublimation of ice, reinforcing the brightness contrast, a feedback loop. The origin of the dark material is still debated. One theory suggests that Iapetus swept up dark dust from outer moons like Phoebe, which orbit in a retrograde direction. As Iapetus orbits through this material, its leading hemisphere gets coated. Over time, the darker surface gets warmer and loses ice, while the trailing side stays cool and bright. It's a case of environmental painting in motion. Iapetus's orbit is highly inclined, tilted about 15 degrees from Saturn's equatorial plane. This makes it somewhat of an outlier among Saturn's major moons. The inclination adds to the mystery. How did Iapetus end up on such a skewed path? Its odd orbit and surface characteristics suggest a unique evolutionary history. Another remarkable feature of Iapetus is its equatorial ridge, a chain of mountains that runs nearly halfway around the Moon's equator. This ridge rises up to 20 kilometers in some areas and gives the Moon a walnut shape. No other large moon has a similar feature. It remains unclear how or why it formed, though several hypotheses exist. One theory suggests the ridge formed from the collapse of an ancient ring that once orbited Iapetus. As the ring's material spiraled in, it may have settled along the equator. Another proposes tectonic uplift, caused by internal processes early in the Moon's history. A third idea is fossil bulging, a remnant shape from when Iapetus was spinning much faster. The ridge is ancient and heavily cratered, meaning it hasn't changed much in a long time. Its preservation tells us that Iapetus has had little geological activity since formation. Unlike Enceladus or Europa, Iapetus shows no signs of current internal activity. Its surface is static, but full of contrast, both visually and structurally. Iapetus also has an unusual rotation period. It takes about 79 days to complete one spin on its axis, the same amount of time it takes to orbit Saturn. This tidal locking means the same face always points toward Saturn, like the Moon does with Earth. It contributes to the thermal and optical asymmetry seen across the surface. Cassini's flybys in the 2000s gave us the most detailed images of Iapetus to date. They revealed fine textures in the dark terrain, showing what appeared to be landslides, ridges, and erosion features. Despite the Moon's ancient stillness, its surface has been shaped over billions of years by impacts and temperature cycling. The contrast in brightness between hemispheres is one of the highest in the solar system. This makes Iapetus a natural laboratory for studying albedo-driven processes, how reflectivity influences temperature and surface evolution. It also illustrates how external forces, like dust from other moons, can dramatically change a body's appearance. Iapetus has no atmosphere, no known subsurface ocean, and no active geology. Yet it continues to attract interest due to its bizarre morphology and orbital dynamics. It represents a very different kind of moon, not geologically alive, but visually and structurally extreme. In its stillness lies a story of collisions, coatings, and contrast. If future missions revisit the Saturn system, Iapetus would offer a unique comparative target. It's not active like Enceladus or Triton, but it holds the most puzzling surface geometry of any major moon. Half black, half white, with a giant ridge across its belly, Iapetus is a frozen paradox, orbiting just far enough away to keep its secrets.
Mimas, the moon that looks like the Death Star and has a wildly oversized crater. Mimas is one of Saturn's smaller inner moons, only about 396 kilometers across, but it's become instantly recognizable due to one feature, the Herschel crater. This massive impact basin spans 130 kilometers, roughly a third of the moon's diameter.
Its sheer size and position give Mimas a resemblance to the Death Star from Star Wars, a comparison often made but not exaggerated. The crater is deep, with steep walls and a central peak rising nearly 6 kilometers from the floor. Scientists believe that if the impact that created it had only been slightly more forceful, Mimas would have shattered. That close call left a scar that defines the Moon's appearance and possibly its internal structure. The event shaped its history in more ways than one. The rest of Mimas is heavily cratered and shows little sign of internal change. It is thought to be geologically dead, with no tectonics, no volcanism, and no current resurfacing. Its low density suggests it's composed mostly of water ice with a small amount of rock. Like many small moons, Mimas lacks the heat needed for sustained activity. But in 2014, scientists analyzing Mimas's rotation noticed something odd. It was wobbling more than expected. This libration hinted at a possible subsurface ocean or an irregular, elongated core. Both possibilities were surprising. Mimas had long been considered inactive, cold, and structurally simple. The idea of an internal liquid layer changed that perspective. Still, subsequent studies have been inconclusive. If Mimas has an ocean, it must be well hidden under a thick, unbroken shell of ice. Unlike Europa or Enceladus, there are no surface signs of water movement, geysers, or cracks. Some researchers now lean toward the idea that the wobble is due to an asymmetric core, not liquid water. Mimas orbits very close to Saturn, inside the densest part of its gravitational influence. This proximity creates strong tidal forces, but not quite enough to warm its interior consistently. It's in a delicate balance, not far enough to escape Saturn's pull, but not close enough to become geologically active. It's a moon caught between states. Mimas is tidally locked, showing the same face to Saturn at all times. This locking, combined with its near-circular orbit, reduces internal friction and heat, explaining its inactivity, but the Herschel crater likely disrupted this balance when it formed. For a time, the impact may have caused global shifts in rotation, tilt, or surface tension. There's also speculation that the Herschel impact may have triggered temporary subsurface melting, enough to create fractures or ice flow. However, no such features are clearly visible today. The crater dominates the hemisphere it occupies, but the rest of Mimas remains quiet, cold, and pockmarked, a surface frozen in time. Despite its modest size, Mimas plays a role in Saturn's ring system. Its gravitational influence helps maintain gaps and wave patterns, especially the Cassini division. These gravitational resonances shape the distribution of ring particles, even though Mimas is distant from the rings themselves. It acts as a small but powerful orbital sculptor. Because of its mass and position, Mimas is also used in orbital models and simulations. Its interaction with other moons, particularly Tethys and Enceladus, help scientists understand resonance chains and orbital evolution in multi-moon systems. Mimas may not change much on its own, but its gravitational pull influences everything around it. No missions have landed on Mimas or studied it in great detail since Cassini's flybys. Still, the idea of a hidden ocean or an asymmetric interior continues to intrigue scientists. If future spacecraft return to Saturn, Mimas might receive closer attention, not just for its crater, but for its quiet complexity. Mimas is often dismissed as just a ball of ice with a big dent, but it may hold surprises under its plain surface. Its defining feature may have almost destroyed it, or momentarily awakened it. Either way, Mimas remains one of Saturn's strangest little moons.
Hyperion, the moon that tumbles uncontrollably and looks like frozen foam. Hyperion is one of Saturn's most unusual moons, not for its orbit or composition, but for its chaotic rotation and porous structure. It's an oddly shaped object, roughly 270 kilometers across, with an appearance that resembles a sponge or pumice stone. Unlike most moons, which have settled into stable rotational states, Hyperion spins erratically, tumbling through space with no fixed axis. This tumbling motion is a result of Hyperion's irregular shape, low mass, and eccentric orbit. The Moon is not a sphere, but a lumpy ellipsoid, which causes its center of mass and center of rotation to constantly shift. Small gravitational nudges, especially from nearby Titan, push it off balance. As a result, Hyperion's rotation is non-periodic, meaning it never repeats the same orientation twice. This makes Hyperion one of the only known large celestial bodies in the solar system with a chaotic rotation. From a physics standpoint, it behaves more like a dice tumbling unpredictably than a neatly spinning top. If a spacecraft were to observe it on two different passes, it would find an entirely different face each time, with no way to predict it. The Moon's surface is equally strange. It's covered in deep, sharp-edged craters that make it look like it's been chipped away over time. But what stands out most is the extremely low density, about 0.55 grams per cubic centimeter, less than water. That means Hyperion is likely highly porous, composed of loosely packed ice and rock, possibly with empty space inside. This spongy consistency may explain why its craters are so deep and well preserved. When impacted, the surface compresses rather than eject material, so there's little debris and no smoothing. Each impact sinks deep into the porous layers, leaving behind sharp holes rather than flat basins. The result is a surface texture like no other moon in the Saturn system. Hyperion's porosity also contributes to its low gravitational cohesion. If spun too fast or disturbed by a significant impact, it could break apart. This makes it an object at the edge of structural stability, held together more by cohesion than gravity. It's not a rubble pile, but it's close. Hyperion is a frozen relic, fragile, oddly shaped, and in constant motion. Its composition is primarily water ice with some darker, carbon-rich material, possibly from meteoric dust. The contrast between light and dark areas make it look unevenly stained, adding to its already irregular texture. Spectroscopic studies show signs of hydrocarbons and organic compounds, though not in large quantities. Hyperion may have absorbed some of this material from Saturn's outer dust ring. Cassini was the only mission to observe Hyperion up close, with a flyby in 2005. The spacecraft captured detailed images of its surface and helped map its chaotic spin. No landers or long-term orbiters have targeted the Moon, mostly due to its small size and unstable orientation. However, its physics remain a valuable case study in rotational dynamics. Hyperion's chaotic spin likely prevents it from maintaining any long-term environmental asymmetries. For example, unlike tidally locked moons, it doesn't have a permanent day or night side. Any internal heating or sublimation would be evenly distributed over time. It's constantly reorienting, meaning no region experiences consistent solar exposure. The Moon's orbit is moderately eccentric, which adds further instability to its motion. Each pass around Saturn slightly alters the gravitational influence it feels, feeding the chaos of its spin. It's locked in a gravitational dance that keeps it forever off balance. Other moons in the system are more stable, but none are quite as unpredictable. Hyperion doesn't influence any major moons or rings, and its gravitational reach is minimal. But in terms of rotational behavior, it remains unmatched.
Its physical properties, from sponge-like density to non-repeating rotation, make it one of the strangest moons in the solar system. It's a celestial oddity floating between stability and collapse. The study of Hyperion has implications beyond Saturn. It helps refine models of how irregular bodies spin, evolve, and retain structure. In a solar system filled with spherical worlds and tidally locked companions, Hyperion spins alone, tumbling forever, never quite the same twice.
An asteroid that looks like a skull and visits Earth on alternating Halloweens. In 2015, astronomers spotted a near-Earth asteroid passing unusually close, just 1.3 lunar distances from our planet. What made this object unforgettable was not just its path, but its appearance. Radar images from NASA revealed an eerie shape. The asteroid looked remarkably like a human skull, complete with eye sockets and jaw contours. It was soon nicknamed the Halloween asteroid. Officially designated 2015 TB145, the asteroid was about 600 meters wide and followed a highly elliptical orbit. Its closest approach occurred on October 31, 2015, Halloween night, adding to its mystique. Its return trajectory would bring it near Earth again in 2018, and it's expected to return again around 2082, depending on small orbital shifts. The asteroid's appearance was likely a coincidence of shadow, surface contours, and low-resolution radar imaging. Still, the resemblance to a skull was unmistakable. Unlike round or jagged bodies, 2015 TB145 had a flattened front and deep concavities, giving it a ghostly silhouette. It was a perfect blend of science and seasonal symbolism. What's more surprising is that 2015 TB145 may not be a typical asteroid at all. Spectral analysis suggests it could be a dead comet, a former cometary nucleus that has lost its volatile ices after many passes near the Sun. Without outgassing or a coma, it now resembles an inert rock. This transformation marks the final stage of cometary evolution. Its dark surface reflects very little light, with an albedo of only about 3 to 6%, making it one of the blackest known near-Earth objects. This low reflectivity made it difficult to detect before its flyby. It was discovered only 21 days before passing Earth, a reminder of how vulnerable we remain to small but close cosmic visitors. The asteroid is classified as potentially hazardous due to its size and proximity, but it poses no current threat. Its orbit is well studied and doesn't intersect Earth's on any near-term timeline. Still, it serves as a case study in how quickly a large object can appear, pass close, and vanish into deep space again, almost without warning. During its 2015 pass, 2015 TB145 was observed using both radar and optical telescopes. High-frequency radar from the Arecibo Observatory provided detailed images of its rotation and shape. It rotates every 5 hours, and its irregular surface likely results from previous impacts or surface loss during its cometary life. It's a relic shaped by both heat and time. The 2018 return was at a greater distance and didn't provide the same visual opportunities, but the nickname stuck, and the skull-shaped visitor became part of public and scientific lore. It's now used in public outreach and astronomy education, a vivid example of how unexpected shapes emerge in space. Sometimes, cosmic coincidence takes on human form. The study of 2015 TB145 also highlighted challenges in asteroid detection. Its late discovery and approach on an orbital plane tilted from Earth's usual surveillance area made it easy to miss. Improving sky survey systems, particularly for off-axis objects, became a renewed priority after its passage.
It was a near miss, not in distance, but in awareness. It also contributed to discussions on planetary defense. If a larger object followed a similar trajectory, we'd have little time to respond. TB-145 became a training case for simulations on rapid response deflection planning, observation coordination, and public communication. It was benign, but ideal for testing readiness. 2015 TB-145 isn't the only oddly shaped asteroid, but few match its skull-shaped profile so well. It doesn't emit light or sound, but it arrived on Halloween with a face that nature sculpted, or at least implied. It's a reminder that space isn't always anonymous. Sometimes it stares back.
Miranda, the moon that looks like it was taken apart and put back together wrong. Miranda is one of Uranus's innermost major moons, and visually, it's one of the strangest bodies in the entire solar system. It looks like a collection of mismatched terrains, stitched together without symmetry or reason. Cliffs, ridges, valleys, and craters all intersect at impossible angles. Its surface defies logic, like geological patchwork in frozen form. The Voyager 2 spacecraft flew by Miranda in 1986, capturing its surface in partial detail. What it found shocked planetary scientists, regions of vastly different ages and structures fused side by side. Some areas were heavily cratered and ancient, while others were smooth and relatively young. It looked as if Miranda had been broken and reassembled. One of the most prominent features is Verona Rupes, a cliff that rises nearly 20 kilometers, one of the tallest known in the solar system. If you fell from its edge, it would take nearly 10 minutes to hit the ground, even with Miranda's low gravity. Features like this aren't common in small moons. Miranda pushes the limits of geological possibility. Its surface also shows grooved coronae, massive oval structures made of ridges and troughs. These coronae appear to be areas where the crust was stretched and resurfaced, possibly by internal convection or ancient tectonic activity. The way these patterns overlay the older terrain adds to the sense of disorder. It's as if Miranda has multiple pasts layered together. How Miranda formed these features is still debated. One theory suggests that it was shattered by a massive impact, and gravity pulled the pieces back together. This reassembly wouldn't be perfect, leading to the mismatched terrain. Another theory favors episodic internal heating, which caused crustal melting and reformation over time. Neither explanation is fully confirmed. Despite its small size, about 470 kilometers across, Miranda appears to have had a complex geological history. This complexity is unusual for small moons, which typically freeze and become geologically inert. Miranda defies that trend, hinting at more internal activity than previously assumed. It forces scientists to rethink how energy can be stored and released in small icy bodies. The source of that energy might be tidal flexing. Miranda is close enough to Uranus to feel its gravitational pull strongly, and this pull varies during its orbit. The stretching and squeezing could generate enough heat to partially melt the interior, triggering the strange surface formations. If so, Miranda would be another example of tidal heating at work. Interestingly, Miranda's orbital inclination is higher than expected, tilted about 4.3 degrees relative to Uranus's equator. This odd tilt may have played a role in its internal dynamics, possibly amplifying tidal stresses. The tilt also raises questions about past interactions with other moons. Miranda may have once been locked in a more chaotic gravitational relationship. Its current orbit is relatively stable, but not perfectly circular.
This means it still experiences some tidal heating, though not enough to produce visible activity today. What we see now is a snapshot of its turbulent past, frozen in place. Any internal activity it once had is likely long gone, leaving only scars and fractures as evidence. Miranda has not been visited since Voyager 2, and our data remains limited. Higher resolution images and spectroscopic studies could reveal whether some features are ice, rock, or a mixture. Understanding its composition is key to understanding how such a small object formed such elaborate terrain. It may hold clues to early moon formation in the Uranian system. Future missions to Uranus, like the ones now being proposed, would likely include a closer look at Miranda. Among Uranus's moons, it's the most visually chaotic and one of the most compelling. Every image raises more questions than it answers. Miranda isn't just unusual, it seems engineered by accident. If one day we explore it up close, Miranda may redefine our understanding of what small moons are capable of. Beneath its jagged surface, it holds a deep record of cosmic violence, geological transformation, and maybe even internal complexity we haven't yet imagined.
The oscillation of Mars's axis and how it shapes climate and colonization. Mars doesn't have a large moon like Earth's to stabilize its tilt. Instead, it wobbles. Its axial tilt, the angle at which it spins relative to its orbital plane, changes dramatically over time, oscillating between about 10 and 60 degrees. This shift is not just a mathematical quirk. It transforms the planet's climate every few million years. These axial shifts are caused by gravitational interactions with the Sun and other planets, especially Jupiter. With no strong moon to counteract these pulls, Mars's rotation becomes unstable over geological timescales. The result is a cycle of chaotic obliquity, where the poles sometimes tip closer to the Sun and then swing away. When the tilt is low, the poles stay cold and icy, and the equator gets the most solar energy. But when the tilt increases, sunlight hits higher latitudes, and the polar ice caps begin to melt or shift. This leads to a redistribution of water and carbon dioxide across the surface. Some researchers believe this cycle helped carve ancient riverbeds. These climate swings may explain layered deposits near the poles, patterns of ice and dust laid down during different tilt phases. It's a kind of geological memory where the Martian surface records its climate cycles. Studying these layers can tell us when Mars was wetter or dustier, and for how long. The idea of axial instability raises concerns for future colonization. A changing tilt means a changing climate, even if it's slow. Over centuries, regions once favorable might become harsh or frozen. Planning long-term habitats will require simulations of Mars's axial future, not just its geography. Today, Mars has a tilt of about 25 degrees, close to Earth's 23.5 degrees, which gives it mild seasons, though much weaker due to its thin atmosphere. But that's temporary. In the distant past, it may have tilted far enough to turn poles into equators. That could have triggered melting events and climate shifts large enough to affect planetary habitability. These tilt variations are also tied to subsurface ice reservoirs. As the planet warms or cools due to changing sunlight angles, ice migrates from pole to equator and back. This hidden water cycle plays a major role in shaping surface features, including gullies, frozen lakes, and permafrost patterns. It also matters for future water extraction. Computer models of Mars's obliquity over time show chaotic trends, unlike Earth's predictable precession. Some simulations predict extreme tilts every few million years, while others show periods of relative stability.
Either way, Mars doesn't stay still. Its axis dances through time, driven by the gravitational tides of the solar system. The presence of former rivers, lakes, and possible shorelines may coincide with past high-tilt eras. If true, understanding Mars's axial history could point us to hidden aquifers or preserved biosignatures. It's not just about climate, it's about where life might have once thrived. The tilt could be the key to targeting future exploration. For future settlers, these changes could affect everything from solar panel angles to crop cycles. Building on Mars will require an adaptive mindset, not just to daily weather, but to long-term planetary rhythms. Colonies won't just be surviving on Mars, they'll be writing its geological metronome. In the short term, the changes are too slow to affect early missions, but over decades and centuries, the oscillating axis will shape Mars's future, both for climate and habitability. Understanding it now helps build a plan for the Mars of tomorrow. It's a slow transformation, but a powerful one. Mars doesn't just spin, it sways, and that sway has carved rivers, buried ice, and may one day decide where humans can thrive or fail.
Herschel Crater, the impact so massive it nearly shattered the moon Mimas. Mimas, one of Saturn's smaller moons, is just 396 kilometers wide, yet it carries a scar that defines its entire identity. This scar is the Herschel Crater, a colossal impact site that spans over 130 kilometers across. That's roughly one-third the moon's entire diameter, making it one of the most proportionally extreme craters in the solar system. At the center lies a towering peak nearly 6 kilometers high, formed from the rebound after the impact. The walls of the crater stretch outward like a shock wave frozen in time. If Earth had a crater of similar proportions, it would stretch across continents. The scale is difficult to grasp. It looks as if Mimas was nearly split in half. The impact that created Herschel was likely powerful enough to almost disrupt the entire moon, perhaps coming just short of total fragmentation. Internal fractures, visible on the opposite side of the moon, suggest the shock traveled all the way through. These cracks aren't surface level, they're structural scars, echoing the violence of that moment. The surface around Herschel is heavily cratered, indicating Mimas has been exposed to countless smaller impacts over time. But none match the size and violence of Herschel. This single event reshaped the moon's geology, perhaps even influencing its internal stability. It's not just a crater, it's a defining wound. The fact that Mimas survived raises questions about its composition and internal cohesion. If it had been made of looser material or had a different density profile, the impact could have shattered it completely. Instead, it held together, barely. This borderline destruction makes it a case study in near-catastrophic survival. Surprisingly, Mimas remains geologically quiet today. No tectonic movement, no volcanism, and no evidence of subsurface oceans like some of its siblings. It appears frozen in time, with Herschel as its central monument. Some theories suggest that, despite appearances, Mimas may still hold surprises beneath its crust, perhaps even a hidden ocean. If so, Herschel may have been the event that altered internal structures enough to trap or expose heat. It's not confirmed, but Mimas has recently been modeled as possibly harboring internal activity based on slight wobbles in its orbit. The giant impact might have done more than scar its surface, it might have shaped its internal dynamics. To many, Mimas resembles the Death Star from Star Wars, a comparison made famous by pop culture. But beyond the visual, the crater represents a real, ancient act of destruction. The moon didn't just survive an impact, it withstood something that could have ended it.
That resilience is scientifically fascinating. The crater was first imaged in detail by Voyager 1 and later by the Cassini mission. Cassini revealed more about its structure, elevation, and fractured terrain. These data allowed scientists to model the impact event and estimate the energy involved. It was the kind of event that reshapes small worlds, both inside and out. Cratering events are common, but few leave marks this dramatic on such small moons. Herschel stands out because of its proportions, the way it dominates the entire moon. It's a rare example where an impact scale borders on the threshold of destruction. That makes it a geological and orbital anomaly. Studying Mimas and Herschel helps scientists understand how much energy a moon can absorb before it breaks apart. It also informs us about asteroid defense, what kind of material composition increases survival chances. Mimas might be quiet now, but it holds a silent record of one of the most violent blows a moon can take. In a system full of smooth spheres and chaotic geysers, Mimas sits quietly with one massive frozen wound. Herschel is more than a crater. It's a moment of violence that almost became extinction.
Phobos, the doomed Martian moon that will become a planetary ring. Phobos is the larger and innermost of Mars's two moons, and it's not going to last forever. In fact, it's slowly spiraling inward, falling closer to Mars by about 1.8 centimeters per year. Eventually, in 30 to 50 million years, it will reach a point where Mars's gravity will tear it apart, turning it into a temporary ring. This process is driven by tidal forces. Because Phobos orbits Mars faster than the planet rotates, it drags against Mars's gravity, losing orbital energy. Earth's moon is drifting away, but Phobos is doing the opposite. It's getting pulled down on a collision course with destruction. It's one of the few moons known to be doing this. The timeline may sound long, but in geological terms, it's fast. When Phobos gets too close, it will cross the Roche limit, the point where gravitational forces from Mars exceed the moon's structural cohesion. At that point, the moon will break apart, scattering debris into orbit. This debris could form a thin, dark ring around Mars. That ring would likely last between 1 million and 100 million years, depending on how the debris behaves. It might be narrow or diffuse, made of fine particles and rocky chunks. For a brief moment in cosmic time, Mars could resemble Saturn with its own ring system, born from a dying moon. Phobos is small, about 22 kilometers across, and irregular in shape, resembling a lumpy potato. It's heavily cratered and marked with long grooves, some of which may already be stress fractures from Mars's gravitational pull. These cracks suggest that tidal stresses are not just theoretical, they're actively reshaping the moon. One of the largest features on Phobos is Stickney Crater, which spans about 9 kilometers, nearly half the moon's width. The impact that created it likely weakened Phobos structurally. Combined with Mars's pull, this makes the moon increasingly fragile. The clock is ticking, and the outcome is inevitable. Phobos's surface is also covered with regolith, a fine dust layer that behaves differently in low gravity. Any shifting or vibration, even from micrometeorite impacts, can cause localized landslides. This surface instability contributes to the moon's erosion and may influence how it eventually breaks apart. The moon's proximity to Mars is extreme. It orbits just 6,000 kilometers above the Martian surface. That's closer than any other major moon in the solar system relative to its planet. Its fast orbit means it crosses the Martian sky in just over 4 hours, multiple times per Martian day. It's the fastest moon in the solar system. Because of its size and orbit, Phobos cannot be a long-term home or base for humans. Its surface gravity is too low, and its lifespan is too short.
However, it could serve as a staging post or be mined for resources before its destruction. Some mission concepts have included robotic landers or sample return missions. The Japanese mission Martian Moons Exploration (MMX) is scheduled to visit Phobos and Deimos in the coming years. It aims to collect surface samples and help determine the Moon's origin, whether it's a captured asteroid or a leftover from Mars's own formation. Understanding its structure will also help predict how it will break apart. In time, Phobos will be no more, but its final act, becoming a Martian ring, will leave a mark on the planet's appearance and dynamics. It's a natural story of decay and transformation, driven not by collision but by inevitable gravitational decay. Mars may one day wear the remnants of its moon like a crown. Phobos is not just falling, it's becoming something new. From moon to ring, its slow collapse is already in motion. The dwarf planet that changes color over the years, and no one knows why. The dwarf planet Makemake, located in the Kuiper Belt, is already unusual for being bright, distant, and airless. But what puzzles scientists is something subtler. Its color appears to change over time. Observations taken years apart show a shift in reflectivity and surface tone, without any clear explanation. It's as if the surface is quietly rewriting itself. Color changes in space often signal seasonal variation, surface chemistry, or atmospheric interactions. But Makemake has no atmosphere to speak of, and its surface temperature hovers near absolute zero. It's too cold for typical geological processes or volatile activity. Yet, its hue fluctuates, going from reddish-brown to lighter and back again. One possible explanation involves volatile ices like methane and nitrogen, which may sublimate or recondense in response to the planet's changing distance from the Sun. Makemake has an elongated orbit that might shift the energy it receives, causing thin frost layers to come and go. Still, the timescales don't align perfectly with the observed changes. Spectroscopic studies indicate that Makemake's surface contains frozen methane and ethane, which are sensitive to cosmic rays and solar radiation. Over time, radiation can break down these compounds and alter their color, forming complex organic residues known as tholins. This might contribute to surface darkening or reddening. However, the data suggest that Makemake sometimes becomes brighter, not just darker. This implies that fresh, reflective material is reaching the surface, possibly through impact events or cryovolcanic resurfacing. But again, there's no confirmed mechanism for such activity. The dwarf planet behaves like it's geologically active, yet there's no proof of motion. The Hubble Space Telescope and other observatories have monitored these changes carefully, noting shifts in albedo, a measure of how much light the surface reflects. These shifts are not random noise. They persist across multiple observations and filter bands. Something is changing on a planetary scale, but slowly and silently. Makemake also has an extremely thin atmosphere that may appear or disappear depending on temperature. This would be transient and difficult to detect, but could alter surface conditions enough to affect its appearance. Even a trace atmosphere, periodically freezing and thawing, might redistribute surface frost. Its rotation is relatively fast for a dwarf planet, just under 8 hours, but shows no clear variation in brightness across one spin. That suggests the color change isn't due to a single region turning or fading, but rather a global surface transformation. This makes the mystery more complex and less about terrain. The discovery of a tiny moon orbiting Makemake adds more intrigue. The moon's influence may cause subtle tidal stress, or its own surface may reflect light in ways that affect the observations. Though unlikely, some researchers have considered gravitational interactions as a possible factor in the color shift. Makemake's brightness also plays a role in how we define and detect other dwarf planets. If such worlds are more dynamic than we thought, then the outer solar system might be far from dead. Each object could be evolving in slow motion, their own kind of quiet weather. Makemake might just be the most obvious case so far. This phenomenon forces astronomers to rethink assumptions about frozen worlds. Are they truly static, or do we just lack the tools to detect their rhythms? Makemake offers a rare chance to observe long-term surface evolution in deep space, something we've barely begun to study. The truth is, we don't know what's causing Makemake to change color. But whatever it is, it's happening on a frozen rock billions of kilometers from Earth, and we're watching it unfold, pixel by pixel. The most reflective object in the solar system, shining like polished ice. The Saturnian moon Enceladus holds an unusual distinction. It's the most reflective body in the entire solar system. Its surface reflects over 90% of the sunlight that hits it, more than freshly fallen snow. This dazzling brightness isn't just for show, it reveals something fundamental about what's happening on and beneath the surface. Enceladus is coated in clean, fine-grained ice that continuously refreshes itself. This isn't old ice that's been weathered by radiation or micrometeorites. Instead, geysers erupt from the moon's south pole, spraying water vapor and icy particles high into space. These particles fall back to the surface, forming a thin layer of pristine snow. Because of this cycle, the surface never has time to grow dull. The ice remains smooth and reflective, creating a mirror-like shine visible even from millions of kilometers away. It's this constant renewal that sets Enceladus apart from darker, more ancient surfaces elsewhere in the solar system. Cassini's instruments confirmed this unusual albedo during multiple flybys. Not only was the brightness uniform, but it was consistent with ongoing geological activity. The plumes themselves are composed of water vapor, ice grains, salts, and organics, a combination that both brightens the moon and points to an ocean below. Most planetary surfaces gradually lose reflectivity due to space weathering, but Enceladus resists this trend. The constant resurfacing from its icy geysers keeps the moon looking fresh, like it was recently cleaned. It's a rare case where brightness is a real-time indicator of activity, not just a frozen remnant. The high reflectivity also affects the moon's thermal properties. Because it reflects so much sunlight, Enceladus remains colder than it otherwise would be. This helps preserve its internal heat, slowing energy loss to space. It's an elegant feedback loop. The surface reflects, the interior stays warm, and geysers keep erupting. Enceladus's brightness even extends into the surrounding space. Its plumes contribute to Saturn's E-ring, and the reflected light from that ring can affect nearby moons and orbits. The moon is not just a passive reflector, it's a source of light-scattering material throughout its region. Its brightness also makes Enceladus easier to detect in images, but harder to analyze in some wavelengths. The reflectivity can saturate detectors and obscure subtle surface variations. Scientists must carefully calibrate instruments to extract meaningful data from such an extreme albedo. The contrast between Enceladus and other moons is stark. Where most icy worlds look dim and gray, Enceladus gleams like a cosmic spotlight. This makes it a visual outlier, but also a scientific magnet, drawing attention to the processes that make it so unique. Models suggest that without its geysers, Enceladus would become darker and colder over time. Its brightness is not a permanent trait, it's a sign of continuous geological life. Stop the plumes, and the mirror fades. This radiant surface is more than just beautiful, it's a signpost. Enceladus isn't just a moon with geysers, it's a bright, reflective signal, telling us something is still happening here.
An asteroid spinning so fast it's breaking apart in real time. Asteroid 2001 OE84 is a near-Earth object, only about 650 meters across, but it's spinning at a dangerously high speed. It completes a full rotation every 29 minutes, making it one of the fastest rotators ever observed. At this pace, its surface material is being flung outward, and the asteroid is at the edge of gravitational cohesion. It's essentially spinning itself to pieces. Most asteroids of this size rotate once every few hours. Going faster than that usually means the object would fly apart unless it's a solid rock. But OE84 seems to defy this expectation. It may be a loosely held rubble pile, held together by weak cohesion, which makes its structural integrity unstable. Observations suggest the asteroid is starting to shed mass, releasing small particles in fragments into space. These could form a cloud or a faint debris trail. If the rotation continues to accelerate, possibly due to solar radiation pressure known as the Oort effect, it could disintegrate entirely within decades or centuries. The Oort effect acts like a cosmic twist. As sunlight strikes the asteroid unevenly, it produces tiny torques over time, which gradually increase its spin rate. This seemingly weak force becomes decisive for small bodies like OE84. It's a silent but relentless accelerator. This phenomenon has led astronomers to monitor OE84 closely, not just because of its instability, but because it's a real-time laboratory for studying asteroid evolution. Watching it break apart gives insight into asteroid mechanics, surface cohesion, and how these bodies age under solar influence. If OE84 fragments, the debris might pose new orbital risks. While the asteroid itself isn't on a collision course with Earth, its broken parts could shift into unpredictable paths. Studying such asteroids helps improve models for planetary defense and impact risk forecasting. What's striking is how subtle the forces at play are. There's no collision, no internal explosion, just sunlight and rotation, slowly pushing the asteroid beyond its structural limits. It's a slow-motion gravitational failure, visible from millions of kilometers away. Some astronomers propose that OE84 could eventually form a binary asteroid, where material thrown off coalesces into a smaller companion. Others suggest it will become a stream of rubble, a failed world disintegrating into dust. Either way, it's undergoing irreversible transformation. Understanding asteroids like this helps plan future missions. A spacecraft encountering OE84 would need to navigate around active debris and loose material, unlike solid, stable targets. It also reveals the dangers of assuming all asteroids are solid. Many are fragile, dynamic systems. Similar fast-rotating asteroids have been found, but OE84 is among the most extreme. It exists at the edge of physical possibility, a cosmic body spinning toward disassembly. The more we observe,
the more we realize how volatile these small objects can be. Eventually, OE-84 may vanish, broken into pieces too small to track. But for now, it offers a fleeting chance to observe the endgame of an asteroid's life cycle. It's not every day we watch a space rock self-destruct in real time. No fire, no sound, no drama. Just speed and the quiet undoing of a world.
The moon that shoots ice jets hundreds of kilometers high without running dry. Enceladus, a small moon of Saturn, is famous for its geysers of water vapor that erupt from cracks near its south pole. These icy plumes shoot material up to 500 kilometers into space, forming vast arcs that feed Saturn's E-ring. What's astonishing is that these jets have been active for decades, maybe longer, without depleting the moon's subsurface ocean. Cassini first detected the plumes in 2005, but they've persisted through multiple observations. The jets emerge from long fractures known as tiger stripes, regions that remain warmer than the surrounding ice. This warmth likely comes from tidal heating, as Saturn's gravity stretches and flexes the moon's interior. Despite the intensity of the eruptions, Enceladus shows no signs of drying out. Models suggest that a global liquid ocean beneath its icy crust is constantly replenished by internal heat and saltwater circulation. This makes the moon not just active, but sustainably active, with a deep reservoir that keeps on giving. Some of the water vapor escapes into space, but much of it falls back onto the surface as fresh snow. This process helps maintain the moon's high reflectivity and fuels the ongoing renewal of its ice shell. It's a closed-loop system with remarkable stability for such a small body. Measurements of the plumes revealed organic molecules, salts, and silicates, all pointing to a potentially habitable environment. The plume chemistry suggests hydrothermal vents at the ocean floor, where water interacts with rock in energy-rich reactions. This makes Enceladus a prime candidate for extraterrestrial life. The scale of these plumes is hard to overstate. Jets burst through ice cracks and reach altitudes higher than the International Space Station's orbit around Earth. That's not just a geological feature, it's a planetary-scale engine powered by gravity and internal motion. These plumes aren't constant, they pulse with tidal cycles. When Enceladus is at certain points in its orbit, the jets become more active, widening the cracks and increasing pressure. This tidal modulation makes the plumes predictable and measurable, which helps in planning future flybys and sample missions. Enceladus doesn't have a thick atmosphere, but the plume spray creates a kind of temporary exosphere. This thin cloud surrounds the moon and contributes material to Saturn's ring system. The exchange of matter between the moon and its planet is an ongoing gravitational partnership. One mystery is how the ice cracks remain open. They should freeze shut in such a cold environment, but internal heat and tidal friction seem to keep the tiger stripes permanently active, preventing the geysers from being sealed off. That's key to their long-term persistence. Cassini flew through the plumes multiple times, effectively sampling the ocean without landing. It collected data on composition, temperature, and density, providing a virtual biopsy of the moon. This non-invasive method opens the door to safe, efficient astrobiological research. Future missions may return to Enceladus with more advanced tools. Some proposals include flying through denser jets or deploying orbiters to monitor variability over time. The goal? Determine not just if water exists, but if something lives inside it. Enceladus keeps erupting, and as long as those plumes keep reaching into space, they offer us a direct window into one of the most promising alien oceans ever discovered.
the interstellar comet that entered the solar system and left without being captured. In 2019, astronomers spotted a visitor unlike anything seen before, a comet named 2I/Borisov, the second confirmed object from outside the solar system to pass through ours. Unlike Oumuamua, this one showed a classic comet tail, a cloud of gas and dust. It was a fully active interstellar comet, burning bright as it raced past the Sun. 2I Borisov came from beyond the reach of our Sun's gravity, arriving on a hyperbolic trajectory. That means it wasn't just passing through on a long elliptical orbit, it was never bound to the Sun and was merely cutting across our solar system like a drive-by traveler. Its velocity and angle confirmed it. This was a true alien object. What made it even more fascinating was how normal it looked. Unlike Oumuamua's bizarre, tumbling shape and non-gravitational acceleration, Borisov behaved like a standard comet, with a nucleus, coma, and tail. That was surprising. It suggested that planetary systems elsewhere also produce icy bodies just like ours. Spectroscopic studies revealed that Borisov was rich in carbon monoxide and cyanide, similar to long-period comets from the Oort Cloud. This composition suggests it formed in a cold, distant region, just like our solar system's own icy outskirts. In other words, it was built under familiar conditions, despite coming from far away. Borisov approached the Sun at around 300,000 kilometers per hour, reached perihelion, and then kept going. The Sun's gravity wasn't enough to capture it, and no planet came close enough to alter its path. It entered and exited in a clean arc, a ghost of rock and ice, disappearing into the void. The most incredible part is how lucky we were to catch it. These objects are tiny, dark, and fast. Spotting one is like catching a bullet with a telescope. The fact that we've now seen two in just a few years suggests interstellar visitors might be more common than we thought. Some researchers hope to build spacecraft fast enough to intercept a future visitor. Missions like Project Lyra imagine launching a probe toward an incoming interstellar object. If successful, we could someday touch a rock born around another star, holding secrets about entirely foreign systems. Borisov shows that the galaxy isn't a closed system. Material moves between stars. Ice, rock, and dust drift across space, carrying traces of ancient worlds, perhaps even prebiotic chemistry. Our solar system isn't isolated. It's part of an ongoing cosmic exchange. The comet was here, and then it wasn't. No capture, no impact, no deflection, just a curve through sunlight and back into night. It reminded us, not everything in our sky belongs to us.
The extreme rotation of an object that spins once every 4 hours. Haumea, a dwarf planet located beyond Neptune, rotates once every 4 hours, making it the fastest spinning large object in the solar system. That's astonishing for a body of its size, over 1,400 kilometers long. The spin is so fast that it's caused Haumea to stretch into an ellipsoid, making it look like a squashed football in space. Unlike most spherical planets and moons, Haumea's rapid rotation distorts its shape, making it significantly longer at the equator than at the poles. This gives it a unique silhouette and complicates efforts to model its interior structure. Scientists believe this shape is stable but fragile, a kind of frozen balancing act. Its spin also creates strange gravity conditions. At the equator, material is flung outward slightly, reducing surface gravity there compared to the poles. If it spun just a little faster, Haumea could break apart. It's balanced at the very edge of what a large object can endure without ripping itself open. So how did Haumea get this way?
One theory suggests a violent impact in the distant past. That collision could have knocked away outer layers and set Haumea spinning at breakneck speed. Supporting this idea is the fact that a family of icy objects shares similar orbits and composition, possibly fragments of that same event. Haumea also has two small moons, which seem to have formed from that ancient debris. These satellites orbit in a way that helps confirm Haumea's spin and mass. Together, they tell a story of destruction, reformation, and extreme motion, all frozen in time. Adding to its mystery is the presence of a ring system, discovered in 2017. It's one of the only known dwarf planets with rings, and they orbit very close to the body. The ring might be stabilized by Haumea's fast rotation, or it may be a leftover from the original collision. Either way, it's another layer of complexity. Haumea's surface is coated in crystalline water ice, which shouldn't naturally form in such a cold region. This hints at internal heating, possibly from tidal interactions or residual energy from its ancient trauma. That would make it more geologically active than previously thought. Because of its fast rotation, observing Haumea is a challenge. Its light curve, the variation in brightness as it spins, shifts rapidly, making precise measurements difficult. But those fluctuations are also the key to understanding its shape, texture, and internal consistency. Some scientists believe Haumea may not be solid all the way through. The rapid spin could allow for layers to shift or deform, especially if it contains a liquid or soft core. That would make it more like a loosely bound collection of icy materials than a rigid sphere. Despite being one of the most exotic objects in the Kuiper Belt, Haumea is still poorly understood. Future missions to this region could change that, offering the first direct look at how speed can shape a world. No other dwarf planet in the solar system spins like this. Its shape, spin, moons, rings, and ice all point to a violent, chaotic past. Yet today, Haumea dances on the edge of destruction, holding together by sheer balance and motion. It's not just fast, it's extreme, and it shows what happens when the physics of rotation push a planet to its limits. Saturn's moon, Hyperion, is one of the strangest objects in the solar system. It's irregularly shaped, looks like a sponge, and has a density so low that it's only about half as dense as water. That means if you had a pool large enough, Hyperion could theoretically float. But more bizarrely, inside it, you might not sink at all. You'd float through loosely packed, frozen dust. Its surface is riddled with deep craters and voids, giving it the appearance of a pumice stone or foam. These craters are unusually sharp-edged, suggesting that when impacts occur, material doesn't collapse or compress, but instead flies away, leaving gaping holes. The surface seems to absorb almost no shock. Hyperion's low density suggests it's a porous rubble pile, a loosely bound cluster of icy material with massive internal voids. Unlike solid moons, Hyperion doesn't have the internal pressure to compact its structure. That's why it's so fragile and bizarrely light, like frozen insulation drifting through space. Its porosity exceeds 40%, which is incredibly high for a celestial body of its size. If you could step onto it, you might find your foot sinking slowly through dust and empty pockets, like walking on crunchy styrofoam. It doesn't have the rigidity of rock or the fluidity of ice, it's something in between. Scientists believe Hyperion is a relic from the early solar system, never fully melted, compressed, or reshaped. It avoided the kind of heating and differentiation that rounded other moons. Instead, it remained in a kind of primordial frozen limbo, stuck between asteroid and moon. Its rotation is equally strange. Hyperion tumbles chaotically through space without a consistent axis. This irregular spin is caused by gravitational interactions with nearby Titan and its own off-kilter shape. As a result, no point on its surface faces Saturn for long. Cassini flybys captured detailed images showing just how bizarre the surface is. Some of the deep craters even appear to reach into the interior. There's little sign of erosion or layering, reinforcing the idea that Hyperion is light, open, and exposed all the way down. Because of its low gravity and porous structure, Hyperion doesn't retain material easily. Particles thrown up from impacts don't fall back. They often escape entirely. That means its surface is continuously chipped away, never able to smooth or seal itself. It also absorbs almost no sunlight, with an albedo of just 0.3, making it darker than you might expect for an icy object. This low reflectivity adds to the mystery, as it suggests a layer of dark material, possibly from cometary dust or radiation-damaged ice, coating its fragile surface. In many ways, Hyperion is a moon that shouldn't exist in this form. It's fragile, unstable, and hasn't been torn apart by gravity. Its survival hints at a delicate orbital balance, or maybe just luck. But while it lasts, it offers a glimpse into what frozen chaos looks like. If you could visit, it wouldn't feel like landing on a rock. It would feel like falling gently into a floating structure of ancient dust and frozen gaps, a ghost of the solar system's beginnings, barely held together. Nereid's orbit is so eccentric, it defies what we know about how moons form. Nereid, one of Neptune's outer moons, follows one of the most extreme orbits of any natural satellite in the solar system. Its path around Neptune is so elongated, or eccentric, that its distance varies by almost 6 million kilometers between closest and farthest approach. That's not normal moon behavior. Typically, moons form from disks of material orbiting their planet, which tends to result in near-circular, equatorial orbits. But Nereid's path is tilted, stretched, and wildly inconsistent. It takes nearly a year to complete one orbit and swings in and out like a celestial slingshot. This has led many scientists to conclude that Nereid didn't form around Neptune, but was captured. That would explain its unstable, eccentric orbit. But the real mystery is, how did it survive the capture process? Moons often crash or shatter when pulled in gravitationally. Nereid seems to have been spared. Its capture may be linked to another moon, Triton, Neptune's largest, which has a retrograde orbit. Some models suggest that when Triton was captured, it disrupted Neptune's original moon system, scattering or destroying earlier satellites. Nereid might be a survivor of that ancient chaos. Despite its eccentric orbit, Nereid is relatively large, about 340 kilometers across, and shows no signs of being torn apart. That suggests it's structurally intact, but also means it's had a surprisingly stable history despite its wild trajectory. It's a contradiction no model fully explains. Nereid's brightness changes unpredictably, which could be due to its rotation, irregular shape, or even shifting shadows from surface features. But some researchers suspect that changes in its orientation during orbit, like how it spins or tilts, may also play a role. Its light curve is erratic, just like its orbit. Its great distance from Neptune also raises questions about how it stays gravitationally bound. The farther a moon is, the more likely it is to be perturbed by solar gravity or nearby planets. Yet Nereid persists, keeping a delicate gravitational tether to its icy host. Infrared studies show a surface composed mainly of water ice, with hints of dust and dark carbon-rich material. It's similar in composition to other irregular moons, reinforcing the idea that it may be a captured Kuiper belt object, drawn in from the edge of the solar system. Because of its strange orbit, Nereid is hard to study close up. Most spacecraft have passed it at great distances, but future missions to Neptune might include flybys or dedicated surveys of this enigmatic moon, which holds clues to Neptune's violent past. In a system that includes retrograde Triton and tiny Proteus, Nereid stands out as a kind of missing link, not quite regular, not entirely rogue. It's a captured outsider that somehow became a long-term resident, defying odds and expectations. The possible existence of rogue planets orbiting perpendicular to the solar plane. The solar system is mostly flat. The planets orbit the Sun within a thin disk, with only slight inclinations. But astronomers have long wondered if some objects break this rule, traveling on paths almost perpendicular to this orbital plane. These would be the so-called rogue or tilted planets, orbiting in secret, far from the Sun. Some models suggest that during the early chaotic phase of the solar system, gravitational encounters with giant planets or passing stars could have flung certain bodies into steep, inclined orbits. If any of these survived without being ejected, they'd now be moving on orbits tilted up to 90 degrees relative to everything else. Evidence for these objects is indirect. Anomalies in the orbits of known bodies like Sedna and 2012 VP113 hint at hidden gravitational influences. Some researchers believe that only an object with mass comparable to Earth or Neptune on a highly inclined path could explain these orbital distortions. Unlike the hypothetical Planet 9, which is theorized to have a broad elliptical orbit aligned with the solar plane, a perpendicular planet would be almost invisible from Earth's perspective. It would spend most of its time far from the ecliptic, where telescopes rarely look. That makes it a prime candidate for remaining undetected. Such a planet wouldn't need to be massive to leave a mark. Even a Mars-sized object drifting in the outer Kuiper belt or beyond could perturb the orbits of small icy bodies. The fact that we see such clustering and tilting in distant objects suggests that something large and misaligned may be lurking out there. If such a body exists, it could be the remnant of a failed planet formation event or even a captured interstellar object that got caught by the Sun's gravity. Some simulations show that planetary systems like ours can snare rogue planets during close stellar flybys in their early years. A perpendicular planet would challenge our understanding of how the solar system formed. It would mean that planetary migration and ejection events were far more violent than previously thought. It might also suggest that the Sun was born in a dense star cluster, where gravitational chaos was common. Detecting such a planet would be difficult. Its orbit would likely keep it far beyond Neptune, reflecting little sunlight, moving slowly, and spending much of its time in obscure sky regions. But next-generation telescopes like the Vera Rubin Observatory might finally catch a glimpse of one. The implications go beyond planetary science. A hidden, steeply inclined planet would reshape our models of solar system stability, long-term evolution, and even the potential for hidden Oort Cloud populations. It could be linked to the mysterious orbits of certain long-period comets. Some have proposed that we widen our survey fields beyond the ecliptic, the orbit of Earth's orbit, to catch objects moving above or below the main planetary disk. If such rogue planets exist, they're not just distant, they're invisible because we're looking in the wrong place. The idea is still speculative, but compelling. It unifies multiple orbital anomalies and matches what we see in exoplanetary systems, many of which contain bodies in wild, misaligned orbits. If those systems have tilted planets, why wouldn't ours? We may never find it, or we may discover that our solar system is more complex than its quiet circular dance suggests, with hidden giants lurking far off the grid.
The moon that tumbles chaotically, never showing the same face twice.
Hyperion isn't just strange for its porous surface, it's also one of the only known moons to spin chaotically, without any regular rotation. Unlike Earth's moon, which always shows the same side, Hyperion tumbles through space in an unpredictable dance. No two rotations are ever the same. This behavior is called chaotic rotation, and it's extremely rare for large celestial bodies. It arises when an object has an irregular shape, an eccentric orbit, and is affected by strong gravitational forces from a nearby body, in this case, Saturn, and its massive moon Triton. Hyperion is shaped like a lumpy potato, not a sphere, which makes its rotational axis unstable. Small gravitational tugs from nearby moons nudge it just enough to send its spin into disarray. Instead of rotating steadily, it flips, turns, and twists in all directions, like a drifting football in zero gravity. When Voyager 2 first passed by Hyperion, it noticed something strange. Every time the moon was observed, a different face was visible. Later studies confirmed that this wasn't just bad timing. The moon was truly spinning without a pattern. It's one of the few large objects in the solar system that behaves this way. The Cassini mission later observed Hyperion in more detail and confirmed that its rotation is not periodic. You can't predict where it will face next. This is not just fast spinning or irregular wobble, it's a form of dynamic instability that arises from nonlinear physics on a celestial scale. Hyperion's orbit is also slightly elliptical, which causes tidal forces to vary across each loop around Saturn. These shifting forces apply uneven torques to the moon, further destabilizing its rotation. It's caught in a gravitational tug-of-war that never settles into a rhythm. Despite its chaos, Hyperion has remained intact for billions of years. That suggests its center of mass and shape are balanced enough to avoid disintegration, even if its motion is unpredictable. It's a durable object trapped in a constantly changing orientation, a frozen body in a spinning maze. Its chaotic spin may prevent temperature extremes from forming on any one side. Unlike tidally locked moons, which bake on one face and freeze on the other, Hyperion spreads out its solar exposure. This could influence surface erosion, ice sublimation, and even the preservation of impact features. Scientists use Hyperion as a natural model for chaotic systems, where tiny changes in conditions produce wildly different outcomes. Its spin helps refine equations in orbital mechanics, especially for small bodies that aren't perfectly round or uniformly dense. The unpredictability also makes Hyperion a difficult target for landers or orbiters. You can't plan for a consistent landing zone because its orientation changes constantly. That makes it less attractive for missions, but more interesting as a scientific curiosity. Other moons with irregular shapes don't show this level of chaos. Hyperion is an exception, balancing on the threshold of stability and randomness. It exists in a narrow space where physics behaves like weather, turbulent and always changing. The formation of the Trojan asteroids, which share Jupiter's orbit like a military formation. The Trojan asteroids are a unique population of objects that share Jupiter's orbit around the Sun. Rather than trailing behind or orbiting separately, they sit in gravitationally stable points known as Lagrange points, specifically L4 and L5. These zones allow the asteroids to maintain their positions 60 degrees ahead of or behind Jupiter, like flanks in a celestial convoy. What makes this setup so strange is that it defies normal orbital logic. You'd expect objects to either fall into Jupiter or drift away, but the Lagrange points create gravitational equilibrium between the Sun and the planet. Objects placed there remain trapped, forming clouds that co-orbit in perfect sync with Jupiter. The leading group is called the Greek camp,
and the trailing group is the Trojan camp, names taken from the Iliad. Each group contains thousands of asteroids, from rocky shards to objects hundreds of kilometers across. Together, they form one of the most unusual and stable swarms in the solar system. These Trojans are thought to be remnants from the early solar system, possibly preserved in their positions for over 4 billion years. Some models suggest they formed closer to the Sun and were captured during Jupiter's migration. Others propose their native debris never part of the planet-building process. NASA's Lucy mission, launched in 2021, aims to explore several Trojan asteroids for the first time. These flybys will reveal the composition, surface features, and history of these mysterious bodies. It's the first attempt to understand what's essentially a fossilized formation frozen in motion around the Sun. The Trojans vary widely in size and type, suggesting they may have diverse origins. Some might be carbon-rich, others metallic. This diversity could mean the Trojans were gathered from different regions of the solar system, offering a cross-section of early planetary material. Their arrangement is so stable that no significant collisions have been recorded, even though thousands of objects occupy relatively narrow orbital zones. This hints at a natural spacing mechanism that prevents overlapping paths, much like schools of fish or organized formations. Not all Trojans are exclusive to Jupiter. Neptune, Mars, and even Earth have Trojan-like companions. But Jupiter's are by far the most massive and populous, and they're the only ones considered dynamically ancient. The others are likely temporary or much younger. The Lagrange points themselves are a broader concept used in space mission design. Satellites and observatories are sometimes placed in similar stable zones, such as the James Webb Telescope in Earth's L2. The Trojans are a natural version of this orbital strategy.